Let's start with Earth itself, our home, the planet beneath your feet right now. From where you're standing, Earth seems absolutely massive, doesn't it? And it is, by human standards. Earth's diameter measures 12,742 kilometers. That's about 7,918 miles, if you're thinking in those terms. You could walk your entire life and never see all of it. The continents stretch for thousands upon thousands of miles. The oceans, vast and deep, cover about 71% of the surface. To someone living their whole life here, Earth feels enormous, infinite, almost. And for most of human history, that's exactly what people believed. Earth was everything, the entire universe. But here's where things start to shift. Because when you actually look at the numbers, when you start examining what Earth really is, something interesting happens. Take Mount Everest, the highest point on our planet. Standing at 8.8 kilometers tall, it seems like an impossibly massive mountain. Climbers spend weeks trying to reach its summit. Many don't make it. Some never come back. It dominates the landscape for hundreds of miles. And yet, Mount Everest's height compared to Earth's diameter is just 0.07%. Let me put that in perspective. If Earth were a basketball, Mount Everest would be like a single grain of sand sitting on its surface. You probably wouldn't even feel it if you ran your hand across it. Think about that for a second. The tallest mountain on Earth, the peak that's become legendary in human culture, is nothing more than a minor bump when you consider the planet's full size. It's barely there at all. Now let's go the other direction. The Mariana Trench, the deepest point in Earth's oceans, plunges down about 11 kilometers below sea level. If you dropped Mount Everest into the Mariana Trench, there'd still be over 2 kilometers of water above its peak. The trench is deeper than Everest is tall. And yet, even this incredible depth is just a scratch on Earth's surface. From the highest mountain to the deepest ocean trench, the total variation is less than 20 kilometers. That sounds like a lot, until you remember that Earth's diameter is 12,742 kilometers. The difference between our highest and lowest points is only about 0.15% of Earth's total diameter. Here's another way to visualize this. If you could shrink Earth down to the size of a billiard ball, something remarkable would happen. All those mountains, all those ocean trenches, all the dramatic terrain that seems so significant to us would vanish. Earth would be smoother than an actual billiard ball, perfectly smooth to the touch. A real billiard ball has tiny imperfections in its surface. Earth scaled down would be smoother than that. The mountains and trenches we consider massive are, in reality, incredibly thin variations on an otherwise smooth sphere. This tells us something important. Earth's surface, the part we live on, the part that contains everything we've ever known, is just a paper-thin layer on a much larger structure. We live on the skin of the planet, and that skin is remarkably smooth. But let's talk about what Earth actually is in terms of mass, because this is where things get interesting for comparison. Earth's mass is approximately 5.97 times 10, circumflex 24 kilograms. That's 5.97, followed by 24 zeros. It's written that way because the actual number is too large to comprehend otherwise. If you tried to write it out fully, you'd need a number with 25 digits. That's an incomprehensibly large amount of mass. Every mountain, every ocean, every building, every person, every animal, every atom of air in the atmosphere, all of it adds up to that number. And we're about to start comparing this to other objects in space. That's when Earth's size starts to become clear. Our first comparison takes us to our nearest neighbor, the Moon, Earth's only natural satellite. The Moon orbits us at an average distance of 384,400 kilometers. That's about 238,855 miles. It seems far, and by everyday standards, it absolutely is. The Apollo astronauts who traveled to the Moon took about 3 days to get there. 3 days of continuous travel through space at speeds we can barely achieve even today. But here's what's interesting about the Moon itself. Its diameter is about 3,474 kilometers. Now, do the math. That's roughly 27% of Earth's diameter. The Moon is about a quarter the size of Earth. If Earth is a basketball, the Moon is roughly the size of a tennis ball sitting beside it. That might not sound that impressive until you realize something crucial. Most moons in the solar system are tiny compared to their planets. Jupiter's moons, Saturn's moons, even Mars's moons are all minuscule relative to their parent planets. But our moon, it's huge in comparison. In fact, the Earth-Moon system is sometimes called a double planet because the moon is so substantial relative to Earth. When you look at volume, the difference becomes even clearer. You could fit about 50 moons inside Earth. Imagine that. Take the moon, duplicate it 50 times, and you could pack all those copies into the space Earth occupies. 50 tennis balls fitting inside one basketball. That's the relationship. But the distance between Earth and the moon reveals something even more fascinating about the scale of space. Remember, the 384,400 kilometers. That distance is enormous. So enormous that you could fit all the planets in our solar system, lined up side by side, in the gap between Earth and the moon. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. All of them would fit in that space with a little room to spare. Think about that. The 8 planets of our solar system, spanning from tiny Mercury to massive Neptune, could all nestle into the distance between us and our closest neighbor. That's how much empty space exists, even in our immediate cosmic neighborhood. And here's another way to grasp that distance. Light, the fastest thing in the universe, traveling at 300,000 kilometers per second, takes 1.3 seconds to make the journey from Earth to the moon. When the Apollo astronauts were on the lunar surface talking to Mission Control back on Earth, there was a 2.6-second delay in their conversations. 1.3 seconds for the signal to travel from Earth to Moon, and 1.3 seconds for the response to come back. It doesn't sound like much, but imagine trying to have a conversation where every response takes nearly 3 seconds to arrive. That delay was a constant reminder of just how far away they were. Now, let's make the comparison that really starts to put Earth in perspective. The Sun, our star, the object that gives us light, warmth, and ultimately, life itself. The Sun's diameter is approximately 1.39 million kilometers. Let me put that in terms of Earth. The Sun is 109 times wider than Earth. If you lined up 109 Earths side by side, they would span the Sun's diameter. But width doesn't tell the full story. Volume does. And the Sun's volume is absolutely staggering. You could fit approximately 1.3 million Earths inside the Sun. 1.3 million. Every mountain, every ocean, every city, every person who has ever lived, all of human history happened on a planet that represents less than 1/1,000,000th of the Sun's volume. Let that sink in for a moment. Earth, which feels so massive to us, which contains everything we've ever known, is just a tiny speck compared to the Sun. And the Sun itself, as we'll discover, is nothing special in the universe. It's just an average star, one of hundreds of billions in our galaxy alone. We're just getting started. Earth seems large when you're standing on it. But as we zoom out, as we start comparing it to other objects, it begins to shrink, and we haven't even left our solar system yet. Let me give you some context about what the Sun really means to our solar system. We just talked about how 1.3 million Earths could fit inside it. But here's the number that truly reveals the Sun's dominance. The Sun contains 99.86% of all the mass in our solar system. Think about that. Everything else, all the planets, all the moons, every asteroid, every comet, every speck of dust floating between the planets, all of it combined makes up only 0.14% of the solar system's total mass. Earth, Jupiter, Saturn, all of them together are basically a rounding error compared to the Sun. We live in the Sun's solar system. Everything else is just debris orbiting around it. Now let's look at the other planets, because comparing Earth to them shows us where we fit in the planetary hierarchy. Start with Mercury, the smallest planet and the one closest to the Sun. Mercury's diameter is only about 4,880 kilometers. That's roughly 38% of Earth's diameter. Mercury is tiny. It's barely larger than our moon. If you stood on Mercury's scorched surface, Earth would seem like a giant world by comparison. But Mercury reminds us that planets come in all sizes, and Earth isn't the smallest thing out there. Venus, on the other hand, is almost our twin, at least in terms of size. Venus has a diameter of about 12,104 kilometers. That's 95% of Earth's diameter. If you placed Earth and Venus side by side, they'd look nearly identical in size. This is why Venus is often called Earth's sister planet. But the similarities end there. Venus's surface is a hellish nightmare of crushing atmospheric pressure and temperatures hot enough to melt lead. Still, in terms of raw dimensions, Venus and Earth are remarkably close. Two planets, nearly the same size, orbiting in the same solar system. Mars is where things get smaller again. The red planet has a diameter of about 6,779 kilometers. That's roughly 53% of Earth's diameter, about half our size. Mars is a cold, desert world with a thin atmosphere and frozen ice caps at its poles. When you look at Mars, you're looking at a planet that's genuinely smaller than Earth. Not dramatically so, but noticeably. If Earth is a basketball, Mars is roughly the size of a soccer ball. But now we come to the giants, and this is where Earth starts to look genuinely small. Jupiter, the king of planets. Jupiter's diameter is approximately 139,820 kilometers. That makes Jupiter about 11 times wider than Earth. 11 Earths lined up side by side would span Jupiter's diameter. When you see Jupiter through a telescope, even through a small one, it's obvious that this is a different category of object. This isn't a rocky planet like Earth. This is a gas giant, a world made mostly of hydrogen and helium, with a mass greater than all the other planets combined. But diameter doesn't capture Jupiter's true scale. Volume does. And here's where the numbers become staggering. You could fit 1,321 Earths inside Jupiter. Not 11, not 100, 1,321. Imagine taking Earth, our entire world, and duplicating it over 1,000 times. All those copies would barely fill Jupiter's volume. Every ocean, every continent, every mountain, every person, duplicated 1,321 times, and it would all fit inside Jupiter with room to spare. Jupiter is so massive that it doesn't just dominate the outer solar system, it affects the orbits of asteroids and comets throughout the entire system. Its gravity pulls on everything nearby. Jupiter is a world on a completely different scale than Earth. Saturn is nearly as impressive. With a diameter of about 120,536 kilometers, Saturn is roughly 9.4 times wider than Earth. It's the second largest planet in our solar system, and like Jupiter, it's a gas giant. Saturn could swallow 764 Earths inside its volume. But Saturn's most distinctive feature isn't its size. It's those magnificent rings. The ring system extends outward from the planet for about 282,000 kilometers. That's nearly 3/4 of the distance from Earth to the Moon. The rings are vast, stretching across a distance that dwarfs most objects in the solar system. But here's what's remarkable about Saturn's rings. Despite spanning such an enormous distance, they're incredibly thin. In some places, the rings are only about 10 meters thick, 10 meters. That's about the height of a three-story building. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. You could almost slice through them with a knife. This shows us something important about cosmic structures. Size doesn't always correlate with thickness or density. The rings are vast but delicate, stretched impossibly thin across space. Uranus takes us even farther out into the cold outer reaches of the solar system. Uranus has a diameter of about 50,724 kilometers, making it roughly 4 times wider than Earth. About 63 Earths could fit inside Uranus by volume, but Uranus is unusual for another reason. It rotates on its side. Most planets spin more or less upright, with their axes roughly perpendicular to their orbital planes. Not Uranus. Its axis is tilted about 98 degrees, which means it essentially rolls around the Sun like a ball rolling along the ground. During part of its orbit, one pole points almost directly at the Sun, experiencing continuous daylight for decades. Then, as Uranus continues its 84-year orbit, that same pole tilts away into decades of darkness. No one knows exactly why Uranus rotates this way, but the most likely explanation is a massive collision early in the solar system's history that knocked the planet over. Neptune, the final planet and the most distant from the Sun, has a diameter of about 49,244 kilometers. That's roughly 3.9 times Earth's diameter. About 57 Earths could fit inside Neptune. Neptune is a frozen blue world, so far from the Sun that it takes 165 Earth years to complete a single orbit. But despite being frozen and distant, Neptune is incredibly violent. Wind speeds on Neptune reach up to 2,100 kilometers per hour. That's about 1,300 miles per hour. These are the fastest winds measured anywhere in the solar system, far exceeding anything on Earth. Hurricanes on Earth, which we consider devastating, have wind speeds around 250 kilometers per hour. Neptune's winds are nearly 9 times faster. Why Neptune, the coldest and most distant planet, has such extreme weather is still something of a mystery. So here's where we stand. Earth, at 12,742 kilometers in diameter, is larger than Mercury, smaller than Venus, and dwarfed by the gas giants. Jupiter alone could contain over 1,000 Earths. Saturn could hold over 700. Even Uranus and Neptune, the smallest of the giants, could each contain dozens of Earths. Our planet, which seems so massive from the surface, is actually one of the smaller worlds in our solar system. We're not the tiniest, but we're far from the largest. And we haven't even begun to look beyond our solar system yet. We're still in our immediate neighborhood, and already Earth is starting to shrink. Let's establish a baseline for measuring distance in our solar system. The distance from Earth to the Sun is approximately 150 million kilometers. That's 93 million miles. This distance is so fundamental to astronomy that it's been given its own unit of measurement, 1 astronomical unit, or AU. Everything in our solar system is measured in AUs. It's our cosmic yardstick. But what does 150 million kilometers actually mean? Here's one way to grasp it. If you could drive a car at highway speeds about 100 kilometers per hour, non-stop, without ever slowing down, it would take you roughly 171 years to reach the Sun. No human has ever traveled that far. No spacecraft has reached the Sun and returned. It's genuinely incomprehensibly distant by everyday standards. Light gives us another perspective. Light travels at 300,000 kilometers per second. That's fast enough to circle Earth 7.5 times in 1 second. And even at that incredible speed, light from the Sun takes 8 minutes and 20 seconds to reach Earth. When you look at the Sun in the sky, assuming you're foolish enough to look directly at it, you're seeing the Sun as it was 8 minutes and 20 seconds ago. If the Sun suddenly vanished right now, we wouldn't know for over 8 minutes. We'd keep receiving its light, keep feeling its warmth, completely unaware that the source had disappeared. The night sky wouldn't go dark immediately. There'd be an 8-minute delay before the universe informed us that our star was gone. Now let's venture to the outer reaches of our solar system. Neptune, the most distant planet, orbits at approximately 30 ATU from the Sun. That's 30 times farther from the Sun than Earth is. At that distance, sunlight takes over 4 hours to travel from the Sun to Neptune. 4 hours. Imagine being on Neptune's frozen surface and watching the sunrise. The light you're seeing left the Sun 4 hours earlier. The Sun you're looking at is the Sun as it was 4 hours ago. Communication with anything on Neptune would involve massive delays. Send a signal to Neptune, and even traveling at light speed, it would take 4 hours to arrive. Wait, another 4 hours for a response. Every conversation would take 8 hours minimum. Beyond Neptune lies the Kuiper Belt, a vast region of icy objects that extends from about 30 ATU to 55 ATU from the Sun. This is where Pluto lives, along with thousands of other frozen worlds. The Kuiper Belt is like a junkyard of the solar system, filled with leftover material from when the planets formed. These objects never coalesced into a planet. They just stayed out there in the cold, orbiting in the darkness. Pluto itself, once considered the 9th planet, gives us a sense of scale for these distant objects. Pluto's diameter is only about 2,377 kilometers. That's roughly 18.5% of Earth's diameter. Pluto is actually smaller than Earth's moon. Our moon has a diameter of about 3,474 kilometers. Pluto wouldn't even qualify as a decent moon if it orbited a larger planet. It's tiny, a frozen ball of rock and ice, barely larger than some of the moons orbiting Jupiter and Saturn. This is why Pluto was eventually reclassified as a dwarf planet. It's just too small, and it shares its orbital space with too many other similar objects. But even the Kuiper Belt isn't the edge of our solar system, not even close. Far beyond, at distances that make Neptune seem nearby, lies the Oort cloud. This is a vast spherical shell of icy objects that surrounds our entire solar system like a cosmic bubble. The Oort cloud extends from about 2,000 AIU to 100,000 AIU from the Sun. Let me put that in perspective. Neptune orbits at 30 AUTA. The Oort cloud begins at 2,000 AUTA. That's more than 65 times farther out than Neptune, and it extends all the way to 100,000 AU. At those distances, the Sun is barely a bright star in the sky. An object in the outer Oort cloud would receive almost no warmth from the Sun. It would be frozen to temperatures just barely above absolute zero. And sunlight? It would take over 19 months to reach the outer edge of the Oort cloud. A year and a half for light to make that journey. This gives us the true diameter of our solar system. Including the Oort cloud, our solar system spans about 2 light-years across. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. Our solar system, from one edge of the Oort cloud to the other, is approximately 2 light-years in diameter. That's the boundary where the Sun's gravitational influence finally weakens enough that objects can drift away into interstellar space. Now here's where the scale becomes truly humbling. Voyager 1, launched in 1977, is currently the most distant human-made object. It's been traveling away from Earth for 47 years, moving at about 61,000 kilometers per hour. That's incredibly fast by human standards. Faster than any other spacecraft we've built. And after nearly half a century of continuous travel, Voyager 1 has covered a distance of approximately 24 billion kilometers. That sounds enormous, and it is. But in cosmic terms, Voyager 1 is only about 0.002 light-years from Earth. It's barely scratched the surface of interstellar space. It's traveled less than 1/10 of 1% of the distance across our solar system. If our solar system were a city 2 kilometers across, Voyager 1 would have traveled only about 2 meters from the center after 47 years. It's barely left the building. And here's the reality that puts everything in perspective. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. Proxima Centauri is 4.24 light-years away. That's more than double the diameter of our entire solar system. At Voyager 1's current speed, traveling at 61,000 kilometers per hour without ever slowing down, it would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. Human civilization as we know it is only about 10,000 years old. Agriculture, cities, writing, all of that happened in the last 10,000 years. Voyager 1 would need 7 times longer than all of human civilization has existed just to reach the nearest star. And it's not even heading toward Proxima Centauri. It's pointed in a different direction entirely. So, it will never get there. This is the reality of interstellar space. The distances are so vast that even our fastest spacecraft, traveling for longer than most human lifetimes, barely makes a dent. The gap between stars is enormous beyond comprehension. And we're about to zoom out even further, because Proxima Centauri, unreachable as it is just one star in a galaxy containing hundreds of billions of them. And Earth? Earth is about to become completely invisible. Let's look at Proxima Centauri more closely, because it reveals something important about stars. Proxima Centauri is what astronomers call a red dwarf. Its diameter is only about 200,000 kilometers. That's roughly 12% the size of our Sun. If the Sun is a basketball, Proxima Centauri is about the size of a tennis ball. It's a small star, much cooler and dimmer than our Sun. In fact, red dwarfs are the most common type of star in the galaxy. Most stars are smaller than our Sun, not larger. But here's what makes red dwarfs fascinating. Because they're so small and burn their fuel so slowly, they live for trillions of years. The universe isn't old enough yet for a single red dwarf to have died of old age. Every red dwarf that's ever formed is still shining today. Alpha Centauri A, another star in the same system as Proxima Centauri, is much more similar to our Sun. Its diameter is about 1.2 times the Sun's diameter, basically the same size. When you look at Alpha Centauri A, you're looking at what our Sun would look like if you were standing 4.24 light-years away. This tells us something crucial. Our Sun isn't special. It's not particularly large or particularly small. It's average. A middle-of-the-road star that sits comfortably in the medium range. For most of human history, we thought the Sun was unique, extraordinary, but it's not. It's just one ordinary star among hundreds of billions. Now let's look at Sirius, the brightest star in our night sky. Sirius appears bright partly because it's relatively close to us, only about 8.6 light-years away. But it's also genuinely larger than our Sun. Sirius has a diameter of about 1.7 times the Sun's diameter. It's roughly 70% larger. If you replaced our Sun with Sirius, Earth would receive significantly more heat and light. Too much, probably. Earth would become uncomfortably hot. But Sirius isn't dramatically larger than our Sun. It's still in the same general category. A main sequence star, burning hydrogen in its core, living a relatively stable life. But now we come to the true giants, stars that make our Sun look pathetic. Betelgeuse, the red supergiant in the constellation Orion, has a diameter approximately 700 times larger than our Sun. 700 times. If you placed Betelgeuse where our Sun is, it would extend past the orbit of Mars. Earth would be deep inside the star, vaporized instantly. Mars would be skimming along just outside Betelgeuse's surface. The inner solar system would simply cease to exist, consumed by this monstrous star. When you look up at Orion on a clear winter night, Betelgeuse is the reddish star marking the hunter's shoulder. It's one of the brightest stars in the sky, and it's so large that if you could somehow stand at a safe distance and look at it, it would fill your entire field of vision. You wouldn't see a point of light. You'd see a vast red sphere dominating the sky. But Betelgeuse isn't even close to the largest star we know. Scuti, one of the largest known stars in the galaxy, has a diameter approximately 1,700 times larger than our Sun. 1,700 times. If Scuti replaced our Sun, it would extend beyond Jupiter's orbit, not just past Mars, not just past the asteroid belt, beyond Jupiter. Saturn would be orbiting just outside the star's surface. Everything closer would be gone, consumed. Let me give you some perspective on Scuti's size. A beam of light traveling at 300,000 kilometers per second would take about 7 hours to circle Scuti once. 7 hours of continuous travel at the fastest speed possible in the universe just to go around this star one time. By comparison, light can circle Earth in about 0.13 seconds. Here's another way to think about it. A commercial airplane flying at cruising speed, about 900 kilometers per hour, would take roughly 1,000 years to fly around Scuti's equator. 1,000 years. Longer than recorded human history. You could start flying when the Roman Empire was at its peak, and you wouldn't finish until long after the present day. And inside Scuti's volume, you could fit approximately 5 billion suns. 5 billion? Take our Sun, which already contains 1.3 million Earths, and duplicate it 5 billion times. That's how much space Scuti occupies. But here's the thing that should truly humble you. Scuti, as incomprehensibly massive as it is still just a single star. One object among hundreds of billions in our galaxy. It's not unique. There are probably other stars just as large or larger that we haven't discovered yet. The galaxy is filled with stars of every size, from tiny red dwarfs barely larger than Jupiter to hypergiants like Scuti that dwarf entire planetary systems. And Earth? At this scale, Earth has vanished. It's not just small, it's non-existent. You couldn't see Earth from Scuti even with the most powerful telescope imaginable. Even our Sun, which contains 1.3 million Earths, is tiny compared to Scuti. Earth is so far below the threshold of significance that the comparison becomes meaningless. Now let's zoom out one more step and look at how our Sun moves through the galaxy. Because even our Sun, our entire solar system, is just one small piece of a much larger structure. The Sun orbits the center of the Milky Way galaxy at a speed of approximately 828,000 kilometers per hour. That's about 514,000 miles per hour. Fast enough to travel from Earth to the Moon in less than half an hour. Our entire solar system, with all its planets, moons, asteroids, and comets, is hurtling through space at this incredible speed. But despite moving so fast, the Sun takes about 230 million years to complete. One orbit around the galactic center. 230 million years. That's called a galactic year, or cosmic year. The last time our Sun was at this point in its orbit, dinosaurs hadn't even appeared yet. The supercontinent Pangaea was still intact. Life on Earth was mostly marine creatures and early reptiles. The time before that, complex life was just beginning to diversify in the oceans. Earth has existed for about 4.5 billion years. That means our planet has completed roughly 20 orbits around the galactic center since it formed. 20 galactic years. The Sun has been around this cosmic track 20 times, and Earth has been along for the ride. But here's what this tells us. Even our Sun, traveling at nearly 1 million kilometers per hour, takes hundreds of millions of years just to go around the galaxy once. The Milky Way is so large that even at these tremendous speeds, it takes eons to traverse. And we're about to see just how large the galaxy truly is. Because we're not done zooming out. Not even close. Our Sun sits approximately 26,000 light-years from the center of the Milky Way galaxy. Remember, 1 light-year is about 9.46 trillion kilometers. That means we're roughly 246 quadrillion kilometers from the galactic center. Even traveling at the speed of light, it would take 26,000 years to reach the center from where we are. Voyager 1, humanity's most distant spacecraft, would need hundreds of millions of years to cover that distance. The Milky Way galaxy itself spans approximately 100,000 light-years in diameter. From one edge of the galaxy to the other is 100,000 light-years. Our solar system sits about 26,000 light-years from the center, which puts us roughly halfway out. We're not in the galactic suburbs, but we're certainly not downtown either. We're in a relatively quiet region called the Orion Arm, a minor spiral arm connecting two larger structures. It's a comfortable location, far enough from the galactic center to avoid the chaos and radiation there, but not so far out that we're isolated. And here's where Earth truly begins to disappear. The Milky Way contains somewhere between 200 and 400 billion stars. Let's use a conservative estimate and say 200 billion. That's 200 billion stars, each one potentially with its own system of planets, moons, asteroids, and comets. Our Sun is one star out of 200 billion. 1. If you tried to point out our Sun from outside the galaxy, you'd have a 1 in 200 billion chance of selecting the right star. And even if you somehow picked the Sun, you'd then have to find Earth among all the planets and objects orbiting it. Here's an analogy that might help. If each star in the Milky Way were represented by a single grain of sand, you'd need multiple Olympic-sized swimming pools to hold them all. 2 or 3 pools, depending on how tightly you packed the sand. That's how many stars we're talking about. And each grain of sand represents an entire solar system, each one potentially with worlds, moons, perhaps even life. And our Sun is 1 grain of sand in those swimming pools. Earth doesn't even register at this scale. It's not a grain of sand. It's a microscopic speck on a grain of sand. The Milky Way's total mass is approximately 1.5 trillion times the mass of our Sun. Remember, our Sun contains 99.86% of our solar system's mass. It's 333,000 times more massive than Earth, and the Milky Way is 1.5 trillion times more massive than that. The numbers become so large they lose meaning. Earth's mass, at this scale, is utterly insignificant. A rounding error on a rounding error. At the center of the Milky Way sits something truly remarkable, a supermassive black hole called Sagittarius A, pronounced Sagittarius A star. This black hole has a mass approximately 4 million times the mass of our Sun. 4 million suns compressed into a region of space so dense that not even light can escape. The event horizon, the boundary beyond which nothing can return, has a diameter about 17 times the Sun's diameter. That might not sound enormous compared to some of the giant stars we've discussed. But remember, this isn't a star, this is a black hole. All that mass, 4 million times the Sun's mass, compressed into a region smaller than the orbit of Mercury. Everything near the galactic center orbits this black hole. Stars zip around it at tremendous speeds. One star, called S2, completes an orbit around Sagittarius A every 16 years, reaching speeds of about 5% of the speed of light. That's roughly 15,000 kilometers per second. These stars are dancing around the black hole in a cosmic ballet, their orbits shaped by gravity so intense it warps space-time itself. But here's something that reveals the true structure of the Milky Way. Despite being 100,000 light-years across, the galaxy's disk is only about 1,000 light-years thick. 1,000 light-years. That's 1% of its diameter. If you made a scale model where the Milky Way was 100 meters across, the disk would be only 1 meter thick. It's incredibly flat, like a dinner plate, or a frisbee spinning through space. This flatness comes from rotation. The galaxy spins, and that spin flattens everything into a disk. The stars, gas, and dust all settle into this thin plane, orbiting the galactic center in roughly the same direction. And our position in this structure? We're in the disk, about halfway out from the center, in a relatively sparse region between major spiral arms. It's a quiet neighborhood. Not much happens here compared to the galactic center or the dense spiral arms where new stars are constantly being born. Now, let me show you where this is all heading. The Milky Way, as vast as it is not alone. It's not even particularly special. There are at least 100 billion galaxies in the observable universe. 100 billion. Each one containing hundreds of billions of stars. The Milky Way is one galaxy out of 100 billion. Our Sun is one star out of 200 billion in our galaxy. And Earth is one planet orbiting that one star in that one galaxy. Do the math. If there are 100 billion galaxies, each containing an average of 200 billion stars, that's approximately 20 sextillion stars in the observable universe. That's 20 sextillion stars. 20 billion trillion. And Earth orbits just one of them. At this scale, Earth isn't small. It's beyond small. It's a concept that barely exists. A speck so tiny that calling it microscopic would be generous. If the Milky Way were the size of North America, our solar system would be smaller than a single blood cell. And Earth would be smaller than an atom in that blood cell. The comparison breaks down because there's simply no way to make it intuitive. We've zoomed from Earth to the Moon, from the Moon to the Sun, from the Sun to the planets, from the planets to the stars, and from the stars to the galaxy. And we're not done. We're about to zoom out even further, to galaxy clusters, superclusters, and the cosmic web that connects everything. And at every step, Earth shrinks. It doesn't just get smaller. It approaches the point where it ceases to have any size at all. Our nearest large galactic neighbor is Andromeda, also called M31. Andromeda sits approximately 2.5 million light-years away from us. That's the distance light, traveling at 300,000 kilometers per second, takes 2.5 million years to cross. When you look at Andromeda through a telescope, or even with your naked eye on a dark night, you're seeing light that left that galaxy 2.5 million years ago, back when early humans were just beginning to use stone tools. The Andromeda you see tonight is Andromeda as it existed long before modern humans walked the Earth. But here's what makes Andromeda particularly interesting. It's not moving away from us like most distant galaxies. It's approaching us at about 110 kilometers per second. That's roughly 250,000 miles per hour. Andromeda and the Milky Way are on a collision course. In approximately 4.5 billion years, the two galaxies will collide. Don't worry about the collision, though. When galaxies merge, the stars are so far apart that actual collisions between stars are incredibly rare. The galaxies will pass through each other, their gravity pulling them back together, until eventually they settle into a single, massive elliptical galaxy. By then, the Sun will likely be dead anyway, so Earth won't be around to witness it. Andromeda is larger than the Milky Way. It contains approximately 1 trillion stars. 1 trillion. That's about 5 times more stars than the Milky Way has. If the Milky Way needed multiple Olympic swimming pools full of sand to represent its stars, Andromeda would need 10 or more. It's a massive spiral galaxy, and in the night sky, if you could see it clearly, it would appear several times larger than the full moon. But it's so faint that you need dark skies to see it at all. The Milky Way and Andromeda aren't alone. They're part of a collection of galaxies called the Local Group. The Local Group contains about 80 galaxies, though most of them are tiny dwarf galaxies with only a few billion stars each. The Milky Way and Andromeda dominate this group. They're the two giants, with everything else being much smaller. Triangulum, the third largest member, has only about 40 billion stars. Still substantial, but nowhere near the scale of Andromeda or the Milky Way. The local group spans approximately 10 million light-years. From one edge to the other is 10 million light-years. Remember, the Milky Way is 100,000 light-years across. The local group is 100 times larger than our galaxy. If the Milky Way were a coin in a scale model, the local group would be about the size of a large room, and within that room, you'd find 80 galaxies, with the Milky Way and Andromeda being the two biggest coins. But the local group itself is just a small cluster within something much larger, the Virgo supercluster. This is an enormous collection of galaxy groups and clusters, containing thousands of galaxies spread across a region of space, approximately 110 million light-years in diameter. The local group is just one small part of this structure, sitting near the outer edge. At the heart of the Virgo supercluster is the Virgo cluster itself, a dense concentration of about 1,500 galaxies located roughly 54 million light-years from us. Imagine the scale here. The Milky Way, with its 200 billion stars, is one galaxy in the local group. The local group is one cluster in the Virgo supercluster, and the Virgo supercluster contains thousands of galaxies, each with hundreds of billions of stars. The numbers become so vast that they stop meaning anything. You can write them down, but you can't visualize them. And here's where it gets stranger. We're not just sitting still in space. We're moving fast. Our entire local group, including the Milky Way and Andromeda, is being pulled towards something called the Great Attractor. We're moving at about 600 kilometers per second toward this gravitational anomaly. That's over 1.3 million miles per hour, fast enough to travel from Earth to the Moon in less than 15 minutes. The Great Attractor is located somewhere between 150 and 250 million light-years away, hidden behind the plane of the Milky Way from our perspective. For decades, astronomers knew something massive was pulling on our galaxy and thousands of others, but they couldn't see what it was. Dust and gas in our own galaxy blocked the view. Using different wavelengths of light, radio waves, infrared, and X-rays, astronomers pieced together what the Great Attractor is. It's not a single object. It's a region of space containing several massive galaxy clusters. The Norma cluster is one of the largest structures in that region. The combined gravity of all those galaxies is what's pulling us. But even the Great Attractor isn't the whole story. Recent observations have revealed something even larger, the Laniakea supercluster. This is our home supercluster, a structure so vast it makes the Virgo supercluster look small. Laniakea, which means immeasurable heaven in Hawaiian, contains approximately 100,000 galaxies spread across about 520 million light-years. The Virgo supercluster, which seemed enormous, is just one part of Laniakea. The Great Attractor is near the center of Laniakea, and everything in this supercluster, including our Milky Way, is slowly flowing toward that central region. Think about that flow for a moment. Our galaxy, which takes 230 million years to rotate once, is drifting through space toward the center of a structure 520 million light-years across. The motion is slow by cosmic standards, but it's inexorable. Gravity, weak as it is over these distances, is still strong enough to move entire galaxies. And Earth's place in all this, we're on a planet orbiting a star in a galaxy that's part of a small group, that's part of a cluster, that's part of a supercluster, that's flowing toward a gravitational center we can barely detect. If you made a scale model where Laniakea was the size of Earth, the Milky Way would be roughly the size of a grain of sand. And Earth would be far, far smaller than an atom. It would be smaller than the smallest subatomic particles we know. The comparison doesn't work anymore because the scales are too extreme. We started this journey standing on Earth, feeling its size beneath our feet. Now we've zoomed out to structures hundreds of millions of light-years across, containing hundreds of thousands of galaxies. and we still haven't reached the edge. We're not done zooming out yet, because Laniakea, vast as it is just one supercluster among many, and all of them together form something even larger. The cosmic web, a structure so immense that Laniakea becomes just one thread in an incomprehensibly vast tapestry. Laniakea, our home supercluster, spans approximately 520 million light-years across. 520 million light-years. If you started traveling at the speed of light when the dinosaurs went extinct 66 million years ago, you still wouldn't have crossed Laniakea yet. You'd need to travel for another 454 million years to make it from one side to the other. This structure is so vast that nothing in human experience can adequately capture its scale. The total mass of Laniakea is approximately 100 million billion times the mass of our Sun. Let me write that out. 100 and quadrillion solar masses. Remember, our Sun contains 333,000 times the mass of Earth. The Milky Way contains about 1.5 trillion suns. Laniakea contains roughly 100,000 Milky Ways worth of mass, all flowing slowly toward a common gravitational center. And within this incomprehensible mass, Earth is so small that it's effectively non-existent. But Laniakea isn't the largest structure we've found, not even close. Let's look at some truly massive galaxies to understand just how extreme the universe can get. IC 1101 is one of the largest known galaxies in the observable universe. Its diameter is approximately 6 million light-years. 6 million. The Milky Way, at 100,000 light-years across, is 60 times smaller. If the Milky Way were a dinner plate, IC 1101 would be the size of a tennis court. This galaxy is so enormous that light takes 6 million years to travel from one side to the other. IC 1101 contains approximately 100 trillion stars. 100 trillion. That's about 500 times more stars than the Milky Way has. If you represented each star in IC 1101 as a grain of sand, you'd need several thousand Olympic swimming pools to hold them all. This isn't just a galaxy. It's a monster, grown over billions of years by consuming other galaxies. It sits at the center of a massive galaxy cluster, and its gravity has pulled in countless smaller galaxies, absorbing them, growing ever larger. But even IC 1101, as incomprehensibly massive as it is just one galaxy, one object in a universe filled with trillions of them. And galaxies don't distribute randomly through space. They cluster along filaments and walls, forming structures that dwarf even the largest galaxies. The Hercules Corona Borealis Great Wall is one of the largest known structures in the observable universe. This is a wall of galaxies, a vast sheet of matter stretching approximately 10 billion light-years across. 10 billion light-years. That's more than 70% of the radius of the observable universe. When you map out the positions of galaxies in this region of space, they form a connected structure, a wall so massive that it challenges our understanding of how the universe works. Here's why that's a problem. According to cosmological principles, the universe should look roughly the same in all directions at large enough scales. There shouldn't be structures so large that they dominate huge portions of the observable universe. But the Hercules Corona Borealis Great Wall exists. It's there, mapped and confirmed. And it's so large that it shouldn't have had enough time to form. The universe is only 13.8 billion years old. Gravity, as strong as it is, shouldn't have been able to pull together a structure 10 billion light-years across in that amount of time. Yet, it exists. This brings us to the ultimate scale, the observable universe, the entire region of space from which light has had time to reach us since the Big Bang. The observable universe has a diameter of approximately 93 billion light-years. 93 billion. That might seem strange. The universe is only 13.8 billion years old, so shouldn't the observable universe be only 27.6 billion light-years across? light traveling for 13.8 billion years in each direction? No, and here's why. The universe has been expanding the entire time. Space itself has been stretching. A galaxy that emitted light 13 billion years ago has moved much farther away during the time its light was traveling toward us. The expansion of space has carried it farther, so the most distant objects we can see are now about 46.5 billion light-years away in each direction. That gives us an observable universe 93 billion light-years in diameter. Within this observable universe, astronomers estimate there are approximately 2 trillion galaxies. 2 trillion, each one containing anywhere from millions to trillions of stars. If you assume an average galaxy contains about 100 billion stars, which is a reasonable estimate, that gives us a total of approximately 200 billion trillion stars in the observable universe. That's 200 and sextillion stars. Let me put that number in perspective. If every star in the observable universe were a grain of sand, you would need several Earth-sized spheres made entirely of sand to represent them all. Not swimming pools anymore, not buildings, entire planets made of sand. And our Sun is one star out of 200 billion trillion. 1. The probability of randomly selecting our Sun from all the stars in the observable universe is effectively 0. It's 1 in 200 billion trillion. That's such a small probability that it might as well be impossible. And Earth? Earth orbits one star out of 200 billion trillion. It's one planet among likely hundreds of billions of trillions of planets. At this scale, Earth doesn't just disappear. It becomes a concept that has no physical meaning. The difference in size between Earth and the observable universe is so extreme that no comparison works, no analogy captures it. If you scaled the observable universe down to the size of Earth, the Milky Way would be smaller than a single atom. Our solar system would be smaller than the smallest subatomic particles we know. And Earth? Earth would be so small that it would fall below the Planck length, the smallest possible meaningful measurement in physics. It would cease to exist as a measurable object. But here's what makes this even more humbling. The observable universe is just what we can see. The actual universe is almost certainly much larger. How much larger, we don't know. It might be a few times larger. It might be thousands of times larger. It might be infinite. If the universe is infinite, then the observable universe, vast as it is, represents exactly 0% of the total. No matter how large 93 billion light-years seems, it's nothing compared to infinity. And in that context, Earth is less than nothing. It's an infinitesimally small speck in an already infinitesimally small visible portion of a potentially infinite cosmos. We started this journey on Earth, standing on solid ground, feeling the planet's size beneath us. Now we've reached a point where Earth has vanished so completely that it's not just invisible. It's conceptually absent from the universe's scale. But we're not quite done, because there's one more perspective to consider, and it's perhaps the most profound one of all. Let's take a moment to truly comprehend what we've discovered. Earth is one planet, orbiting one star, in one galaxy, among approximately 2 trillion galaxies in the observable universe. 1 out of 2 trillion, and that one galaxy contains 200 billion stars, most of which likely have their own planets. The odds of Earth being randomly selected from all the worlds in the observable universe are so astronomically small that the number is essentially meaningless. Here's a comparison that might help, though even this falls short. The number of stars in the observable universe, roughly 200 billion trillion, exceeds the total number of grains of sand on all of Earth's beaches combined. Every beach, every desert, every sandy shore on our entire planet. Count every single grain, and you still wouldn't reach the number of stars in the universe. And each of those stars could have planets, moons, asteroid belts, entire solar systems. The scale defies human comprehension. Now consider what we're actually seeing when we look at the distant universe. Light from the edge of the observable universe has traveled for approximately 13.8 billion years to reach us. When you look at the most distant galaxies visible in our deepest telescope images, you're not seeing those galaxies as they are today. You're seeing them as they were 13.8 billion years ago, shortly after the Big Bang. The light left those galaxies when the universe was young, and it's been traveling through space ever since, finally arriving at Earth in our lifetime. This means we're looking back in time. The deeper we look into space, the further back in time we see. Those distant galaxies might not even exist anymore in the form we observe them. They've had 13.8 billion years to evolve, to merge with other galaxies, perhaps to fade away entirely. But we'll never know. The light showing us their current state won't reach Earth for billions of years. We're seeing the universe's past, frozen in light that's been traveling for eons. The most distant observed galaxy is located approximately 13.4 billion light-years away. This galaxy formed only about 400 million years after the Big Bang. We're seeing it as it existed when the universe was just 3% of its current age. This galaxy is a snapshot of the early universe, a glimpse of what galaxies looked like when the cosmos was still young and chaotic. Stars were forming at incredible rates. Heavy elements were scarce. The universe looked fundamentally different than it does today. But here's something that should make you pause. The observable universe is just what we can see. There's almost certainly more universe beyond that cosmic horizon. Much more. The actual universe could be far larger than the observable portion. It could be thousands of times larger, millions of times larger, or it could be infinite, extending forever in all directions. If the universe is infinite, then everything we can observe, all 93 billion light-years of it, all 2 trillion galaxies, represents exactly 0% of the total. Infinity has a way of making even the largest finite numbers irrelevant. And here's where it gets stranger. The cosmic horizon, the boundary of what we can potentially see, is expanding. Every day that passes, light from objects one light day farther away has time to reach us. The observable universe grows by about 1 light day in radius every day. You'd think this means we'll eventually see everything, right? Just wait long enough, and the light from increasingly distant objects will arrive. But no, because space itself is expanding. And at extreme distances, space is expanding faster than the speed of light. That might sound impossible. Nothing can travel through space faster than light, after all. But space itself isn't constrained by that rule. Space can expand at any rate. And in the distant universe, regions of space are receding from us faster than light can travel through space. This means there are galaxies we will never see, no matter how long we wait. Their light is trying to reach us, but the expansion of space is carrying them away faster than their light can close the distance. They're beyond our cosmic horizon permanently. The universe is expanding at a rate described by the Hubble constant, approximately 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. What this means is that for every 3.26 million light-years of distance, space is expanding at an additional 73 kilometers per second. The farther away something is, the faster it's receding from us. Not because it's moving through space, but because the space between us is expanding. At about 14 billion light-years away, objects are receding faster than the speed of light due to this expansion. We can still see some of them because the light was emitted when they were closer, and it's been traveling toward us ever since. But anything much farther than that is gone, forever. Its light will never reach us because the expansion is too fast, and the expansion is accelerating. Some mysterious force, called dark energy, is pushing space apart at an increasing rate. This means the universe's expansion will get faster and faster over time. Eventually, even relatively nearby galaxy clusters will be carried beyond our cosmic horizon. In approximately 1 trillion years, only the galaxies that are gravitationally bound to our local group will still be visible. Everything else will have receded beyond observation. The Virgo supercluster, the Great Attractor, Laniakea, all of it will be gone from view. Future astronomers, if any exist, will look out and see only a handful of nearby galaxies. The rest of the universe will have vanished, hidden beyond an ever-expanding cosmic horizon. They'll have no way to know that trillions of other galaxies once existed within view. No way to discover the Big Bang because the evidence will be too faint or gone entirely. They'll live in what appears to be a small, lonely universe. Unless they find our records, they'll never know how vast the cosmos truly is. This is the ultimate fate of observation in an accelerating universe. We live in a unique time, a time when the universe is old enough for galaxies to have formed and for intelligent life to have evolved, but young enough that we can still see the distant cosmos. We can still observe the cosmic microwave background, the afterglow of the Big Bang. We can still measure the universe's expansion and deduce its history. Future civilizations, trillions of years from now, won't have that luxury. So here we are, standing on Earth, one planet among countless trillions, in a universe so vast that even the observable portion defies comprehension, looking out at galaxies whose light has traveled for billions of years to reach us, seeing the past, watching the universe evolve, and knowing that what we can see is only a tiny fraction, possibly an infinitely small fraction, of everything that exists. Earth, in this context, is beyond insignificant. It's so small that no words adequately describe it. And yet, it's also precious, because as far as we know, Earth is the only place in all that vastness where life exists, where consciousness has emerged, where beings like us can look out at the cosmos and comprehend at least partially the true scale of everything. That's both humbling and remarkable. We're tiny, but we're also aware, and that awareness might be the rarest thing in the universe. Let's shift our perspective for a moment and think about Earth in terms of volume. Pure physical space. Earth's volume is approximately 1 trillion cubic kilometers. 1 trillion. That sounds absolutely massive, doesn't it? And by human standards, it is. You could fit every building ever constructed, every city, every structure humanity has ever created, and still have room for trillions more. From our perspective, Earth's volume is essentially infinite. We could never fill it. But now compare that to the Sun. The Sun's volume is approximately 1.4 million times larger than Earth's volume. Everything Earth contains, all that space, could be duplicated 1.4 million times, and it would all fit inside the Sun. The difference is so extreme that Earth becomes negligible. 1 trillion cubic kilometers sounds huge until you realize the Sun could contain 1.4 million trillion cubic kilometers. Now let's zoom out to the Milky Way's volume. And here's where things become truly incomprehensible. The Milky Way spans 100,000 light-years across and is roughly 1,000 light-years thick. The volume of that disc-shaped region is so enormous that comparing it to Earth becomes meaningless. But what's even more remarkable is that the Milky Way is mostly empty space. The stars, despite numbering in the hundreds of billions, are so far apart that if you traveled through the galaxy, you'd spend almost all your time in the void between them. The volume is incomprehensibly large, but most of it contains nothing. Here's a scale model that might help. If you shrunk the Sun down to the size of a white blood cell, about 10 micrometers across, the Milky Way on that same scale would be approximately the size of the United States, the entire continental United States. That's how much larger the galaxy is compared to our Sun. And remember, Earth would be far too small to see at that scale. It would be smaller than any particle you could detect. Let's try another model. If you could shrink the Milky Way down to 100 meters across, roughly the length of a football field, Our entire solar system would be about 1 millimeter in diameter. 1 millimeter. About the thickness of a credit card. Everything we've ever explored, every planet we've observed, the sun, the Kuiper Belt, all of it would fit in a space smaller than a pinhead. And Earth on that scale, Earth would be completely invisible. Even under the most powerful microscope, you couldn't see it. It would be far smaller than the wavelength of visible light. You couldn't detect it with any optical instrument. The planet that feels so solid beneath your feet, the world that seems so vast, would vanish entirely at the scale of the galaxy. But here's something that reveals an even stranger truth about scale and space. Let's zoom in instead of out. Let's look at what Earth is made of. Your body, the ground beneath you, everything around you. It's all made of atoms. And atoms, despite feeling solid, are almost entirely empty space. An atom consists of a nucleus at the center, containing protons and neutrons, surrounded by a cloud of electrons. But the nucleus is incredibly tiny compared to the overall size of the atom. Approximately 99.999% of an atom's volume is empty space. If an atom were the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. Everything else, all that space between the nucleus and the outer edge of the atom, where electrons exist, is emptiness. Yet atoms feel solid. When you touch something, you're not actually making contact with its atoms. What you're feeling is the electromagnetic repulsion between the electrons in your hand and the electrons in the object. The electromagnetic force prevents the atoms from getting too close. It creates the sensation of solidity, even though there's no actual physical contact happening. You've never truly touched anything in your life. You've only felt the repulsive force between electron clouds. Now, let's go smaller. A proton, one of the particles in an atom's nucleus, is approximately 100,000 times smaller than an atom. The ratio between a proton and an atom is similar to the ratio between a marble and a football stadium. If you placed a marble at the center of a stadium, that's roughly the size comparison. The proton is the marble, the atom is the stadium. And remember, the stadium is mostly empty. This means that matter, the stuff you think of as solid, is almost entirely void. Your body, which feels substantial, is 99.99999% empty space. The chair you're sitting on, the ground beneath your feet, the walls around you, all of it is mostly nothingness held together by electromagnetic forces. If you could somehow remove all the empty space from the atoms in your body, compressing everything so that the protons, neutrons, and electrons were touching, your body would be smaller than a grain of sand. All of you, everything that makes you who you are, would fit in a space about the size of a dust particle. This reveals something profound about the universe. Scale works in both directions. Zoom out, and Earth becomes vanishingly small compared to stars, galaxies, and the cosmos. Zoom in, and Earth, along with everything in it, becomes mostly empty space held together by forces we can't see. In both directions, the universe is far emptier and far stranger than our everyday experience suggests. Let's go even smaller than protons, down to the fundamental building blocks of matter. Quarks. Quarks are the particles that make up protons and neutrons. They're at least 10,000 times smaller than a proton. At least. We say at least because quarks might actually be point particles with no size at all, but our instruments can't measure anything smaller than about 10 circumflex 19 meters. That's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 meters. Quarks are so small that they exist at the very edge of what we can possibly detect. Now here's something remarkable about scale. The observable universe is approximately 10 circumflex, 27 meters across. That's 1 sextillion, 0.00000 meters. A quark, as far as we can tell, is about 10 circumflex 19 meters. Human beings, standing at roughly 1 to 2 meters tall, sit almost exactly in the middle of this scale. We're about as large compared to quarks as the observable universe is compared to us. We exist at the geometric midpoint between the smallest and largest things we know. This means our perspective is uniquely positioned. We're not at the extreme of either scale. We're in the middle, able to contemplate both the incomprehensibly large and the incomprehensibly small. It's a strange place to be. Neither giants nor specks, but something in between. Let's shift back to time, because scale isn't just about space. It's also about duration. There are more stars in the observable universe, roughly 200 billion trillion, than seconds that have passed since the Big Bang. The universe is 13.8 billion years old. That's about 4.4 times 10 circumflex 17 seconds, 400 quadrillion seconds. And yet the number of stars, 2 times 10 circumflex 23, exceeds that. The universe hasn't existed long enough for there to be 1 second of time for every star. If you started counting stars at the moment of the Big Bang, counting 1 per second, you still wouldn't have counted them all by today. Earth has existed for approximately 4.5 billion years. The universe is 13.8 billion years old. That means Earth has existed for only about 33% of the universe's total lifespan so far. Wait, let me recalculate that. 4.5 divided by 13.8 is about 0.326, or 32.6%. But here's where it gets more humbling. If we're talking about the universe's total lifespan, including its future, Earth's existence becomes a blip. The universe will continue for trillions upon trillions of years. Stars will keep forming for another 100 trillion years or so. Earth's 4.5 billion years represents only about 0.03% of the time from the Big Bang to now. Humanity has existed for approximately 300,000 years, if we're counting modern Homo sapiens. That's 0.0022% of the universe's age. Actually, let me be more precise. 300,000 divided by 13.8 billion is 0.0000217, or about 0.0022%. We've been around for 0.002% of cosmic history. We showed up just moments ago on the universe's timeline. All of recorded human history, from the earliest written records about 5,000 years ago to today, represents approximately 0.00004% of the universe's age. Everything you've ever learned in history class, every civilization that rose and fell, every empire, every war, every discovery, all of it happened in the last 0.04% of the universe's existence. And your lifetime? If you live 80 years, that's roughly 0.000000005% of the universe's age. About 6 billionths of 1%. You exist for the blink of an eye, on cosmic timescales. The universe was here for 13.8 billion years before you arrived, and it will be here for trillions of years after you're gone. Your entire life, every moment you've experienced, every memory you have, occurs in a time frame so brief that it barely registers against the cosmic clock. This brings us back to that profound image from 1990, the pale blue dot. Voyager 1, after completing its primary mission, turned its camera back toward Earth from a distance of approximately 6 billion kilometers. That's about 40 times the distance from Earth to the Sun. From that vantage point, Earth appeared as a tiny speck of light, less than a single pixel in the photograph, a pale blue dot suspended in a beam of scattered sunlight. Carl Sagan reflected on this image with words that still resonate today. Every human who has ever lived on that dot. Every king and peasant, every hero and coward, every civilization that flourished and fell, every idea ever conceived, every emotion ever felt, all of it happened on that barely visible speck. Every war was fought over some fraction of that dot. Every triumph and tragedy played out there. And from just 6 billion kilometers away, a distance that's nothing on cosmic scales, Earth was already almost invisible. From the nearest star, you couldn't see Earth at all. From another galaxy, you couldn't see our sun. From the far side of the universe, the entire Milky Way would be just one faint smudge of light among trillions of others. And Earth would be so impossibly small that the concept of its size would cease to have meaning. In the cosmic scale, Earth is unimaginably small. We've explored this from every angle. Compared to planets, compared to stars, compared to galaxies, compared to superclusters, compared to the observable universe itself. At every step, Earth shrinks until it effectively disappears. If the observable universe were compressed to the size of Earth, the Milky Way would be smaller than an atom. And Earth would be so far below any measurable scale that it would exist only as a mathematical abstraction. And yet, despite all of this, despite Earth's incomprehensible smallness, despite existing for only the briefest moment in cosmic time, despite being one planet among potentially trillions upon trillions, despite all of that, Earth is infinitely precious. Because as far as we know, Earth is the only place in the entire observable universe where life exists, the only place where matter has organized itself into living systems, the only place where consciousness has emerged, the only place where beings exist who can look out at the cosmos and comprehend their own cosmic insignificance. This might not be unique. There might be billions of other worlds with life. There might be countless civilizations scattered across the galaxies, all looking up at their own skies and wondering if they're alone. But we don't know that. Right now, with all our telescopes and all our searching, Earth remains the only confirmed example of life in the universe, which means that every living thing on this planet, every species, every ecosystem, every person represents something that might be extraordinarily rare or even unique. Size doesn't determine value. What matters isn't how big something is, but what it contains. And Earth contains something remarkable. Life, complexity, consciousness, the ability to wonder, to question, to seek understanding. In a universe that's mostly empty space, mostly cold and dark and lifeless, Earth is a refuge of warmth and light and activity. A small island of organization in an ocean of entropy. We are tiny, impossibly, incomprehensibly tiny. But we're also aware we can understand the universe's scale even though we occupy almost none of it. We can look out at structures billions of light years across and comprehend them. We can look inward at quarks and atoms and understand them too. We exist at the midpoint of scale, witnesses to both the vast and the minute. Earth might be small. Your life might be brief. But right now, in this moment, you're part of something extraordinary. You're standing on the only known world where the universe has become conscious of itself, where matter has arranged itself in such a way that it can think, feel, create, and understand. That's not insignificant. That might be the most significant thing in the entire cosmos. So yes, Earth is unimaginably small, but Earth is also home. And sometimes that's enough. Let's talk about the sheer power of the sun. Every single second, the sun converts approximately 4 million tons of matter directly into energy through nuclear fusion. 4 million tons. Every second. This isn't fuel being burned in the traditional sense. This is matter itself being transformed into pure energy according to Einstein's equation. E equals mc squared. The mass literally disappears, converted into the light and heat that keeps our solar system alive. And here's what makes that staggering. In just 1 second, the sun produces more energy than all of humanity has used throughout our entire history. Every fire ever lit, every power plant ever built, every engine ever run, every light bulb ever switched on, all of it combined doesn't equal what the sun produces in a single second. We could take all the energy humanity has consumed since we first learned to make fire hundreds of thousands of years ago, add it all together, and it wouldn't match 1 second of the sun's output. Let's return to numbers that challenge comprehension. There are more stars in the observable universe than all the words ever spoken by every human who has ever lived. Think about that. Every conversation, every speech, every whisper, every shout, every word uttered by approximately 100 billion humans throughout history. Estimate that each person speaks, on average, 860 million words in their lifetime. That's about 86 quintillion words total across all of human history. The number of stars in the observable universe is approximately 200 billion trillion. That's 200 sextillion. There are more than 2,000 stars for every word ever spoken. Now, let's look at objects that reveal just how extreme physics can become. Neutron stars. When a massive star explodes as a supernova, its core can collapse into a neutron star. This is a sphere of matter so dense that it defies everyday intuition. A typical neutron star contains approximately 1.4 times the mass of the Sun, all of it compressed into a sphere only about 20 kilometers in diameter. 20 kilometers. That's roughly the size of a large city. Imagine crushing the entire Sun, which is 1.4 million kilometers across, down to the size of Manhattan. The density is incomprehensible. 1 teaspoon of neutron star material, if you could somehow scoop it up and bring it to Earth, would weigh approximately 6 billion tons. 6 billion. A single teaspoon. That's roughly the weight of all humans on Earth combined, crushed into a volume that would fit in your hand. The atoms have been compressed so tightly that electrons have merged with protons, forming neutrons. The star is essentially one giant atomic nucleus. Gravity on a neutron star's surface is approximately 2 billion times stronger than Earth's gravity. 2 billion times. If you weigh 150 pounds on Earth, you'd weigh 300 billion pounds on a neutron star's surface. Of course, you'd never actually stand on a neutron star. You'd be crushed instantly into a thin layer of atoms spread across the surface. The gravity is so intense that nothing resembling a human body could exist there. Some neutron stars spin fast. The fastest spinning neutron star we've detected rotates approximately 716 times per second. 716 rotations every second. In the time it takes you to blink, this object, a city-sized sphere containing more mass than the Sun, has spun around hundreds of times. The surface is moving at a significant fraction of the speed of light. These objects are called pulsars because they emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like cosmic lighthouses. But here's where neutron stars become truly terrifying. If you somehow survived long enough to fall toward one, you'd experience something called spaghettification. The gravity at your feet, which would be slightly closer to the neutron star than your head, would be so much stronger than the gravity at your head that the difference would literally stretch you. The tidal forces would pull you into a thin stream of atoms, elongating your body until you resembled a piece of spaghetti. Then that spaghetti would be torn apart into individual atoms, and those atoms would be crushed into the neutron star's surface. This would happen in fractions of a second. Then there are magnetars. These are neutron stars with magnetic fields so strong they break physics as we normally understand it. A magnetar's magnetic field is approximately 1 quadrillion times stronger than Earth's magnetic field. That's 1 quadrillion times stronger. These are the most magnetic objects known in the universe. How strong is that field? Here's a way to understand it. If a magnetar were located halfway between Earth and the Moon, roughly 190,000 kilometers away, its magnetic field would be strong enough to erase every credit card, hard drive, and magnetic storage device on Earth. Instantly, every piece of data stored magnetically would be scrambled. Your credit cards would become useless. Computer hard drives would be wiped. The magnetic field is so intense, it would interact with the electrons in atoms, distorting their orbits. But it gets worse. If you were within about 1,000 kilometers of a magnetar, the magnetic field would be strong enough to disrupt the molecular bonds in your body. The atoms that make up your cells would be pulled apart by magnetic forces. Your body would literally disintegrate at the atomic level. This isn't science fiction. This is what happens when magnetic fields reach these extreme intensities. Magnetars occasionally have what are called starquakes. The crust of the neutron star, under enormous stress from the magnetic field, cracks and shifts. When this happens, the magnetar releases a burst of gamma rays and X-rays, so intense that it can be detected across the galaxy. In December 2004, a magnetar about 50,000 light-years from Earth had a starquake. The burst of radiation reached Earth and temporarily disrupted our planet's ionosphere. This was from an event 50,000 light-years away. If that magnetar had been within a few dozen light-years of us, the radiation could have caused a mass extinction. These objects, neutron stars and magnetars, show us what happens when matter is pushed to its absolute limits. They're the remnants of massive stars, compressed to densities where physics becomes extreme. And they remind us that the universe contains phenomena so violent and powerful that Earth's entire existence could be snuffed out by events happening light-years away. We think of Earth as solid and permanent, but in a universe filled with supernovae, magnetars, black holes, and gamma-ray bursts, Earth's survival is somewhat fortunate. We exist in a relatively quiet region of the galaxy, far from the most violent events. If we were closer to the galactic center, or if a nearby star went supernova, Earth's story might have ended long ago. This is another dimension of Earth's smallness. We're not just small in size, we're fragile, vulnerable to cosmic events over which we have no control. A gamma-ray burst pointed in our direction could sterilize half the planet. A nearby supernova could strip away our atmosphere. A rogue star passing through the solar system could disrupt planetary orbits. We exist at the mercy of a violent universe, sheltered only by distance and luck. And yet, here we are, still here, still alive, still conscious. Earth might be small and fragile, but it's endured for 4.5 billion years. Life has survived multiple mass extinctions. Consciousness emerged despite the odds. We're not just tiny, we're also resilient. And that resilience, in the face of cosmic indifference, is something worth acknowledging. Let's talk about the most extreme objects in the universe. Black holes. We've mentioned them before, but now let's truly grasp what they are. Black holes can have masses billions of times greater than our sun. Not thousands, not millions, billions. These aren't just massive objects. They're gravitational monsters that warp space-time so severely that nothing, not even light, can escape once it crosses the event horizon. TON 618 is one of the most massive black holes ever discovered. An ultramassive black hole with approximately 66 billion times the mass of our Sun. 66 billion. Take the Sun, which already contains 1.3 million Earths, and multiply its mass by 66 billion. That's TON 618. The scale is so extreme that the black hole itself defies visualization. The event horizon of TON 618, the boundary beyond which nothing can escape, is approximately 1,300 astronomical units across. Remember, 1 AU is the distance from Earth to the Sun. Neptune orbits at about 30 ATU. TON 618's event horizon extends to 1,300 ATU. That's 40 times farther out than Neptune's orbit. If you place TON 618 where our Sun is, its event horizon would extend far beyond our entire solar system. The Sun, all the planets, the Kuiper Belt, even a significant portion of the Oort cloud, all of it would be inside the event horizon. Consumed. Light, traveling at 300,000 kilometers per second, would take approximately 2.5 weeks to cross from one side of TON 6 event horizon to the other, 2.5 weeks. Light crosses Earth's diameter in about 0.04 seconds. It crosses the Sun in about 4.6 seconds. But TON 618's event horizon is so vast that light needs weeks to traverse it, and TON 618 isn't even the largest. Phoenix A, another ultramassive black hole, is estimated to have a mass of approximately 100 billion times the Sun's mass. 100 billion solar masses. The event horizon would be even larger, perhaps 2,000 AUA or more. These objects are so massive that they dominate entire galaxies. They sit at the centers of galaxy clusters, pulling in matter from all directions, growing larger over billions of years. But here's what puzzles scientists. These supermassive black holes formed less than 1 billion years after the Big Bang. The universe was young, only about 600 to 800 million years old, and somehow, black holes with masses of billions of suns already existed. How? Black holes form when massive stars collapse, creating black holes maybe 10 or 20 times the Sun's mass. Then they grow by consuming matter or merging with other black holes. But that process takes time, a lot of time. There shouldn't have been enough time in the early universe for black holes to reach billions of solar masses. Yet they exist. We've observed them. Their light, or rather the light from matter falling into them, has traveled across 13 billion light-years to reach us. Scientists are still trying to understand how these monsters formed so quickly. Did they start as much larger seed black holes? Did they grow faster than our models predict? We don't know. It's one of the major unsolved mysteries in astrophysics. Now let's talk about what happens near a black hole, because the physics becomes genuinely strange. At the event horizon, time itself behaves differently. If you were watching someone fall toward a black hole from a safe distance, you'd see them slow down as they approached the event horizon. From your perspective, they'd appear to take longer and longer to move. As they reached the horizon, they'd seem to freeze, their image getting dimmer and redder until they faded from view entirely. Time, from your perspective, appears to stop at the event horizon. But from the person's perspective, they'd experience nothing unusual as they crossed the horizon. To them, time flows normally. They'd cross the event horizon in finite time and continue falling inward. The difference in perspectives is real. Time genuinely flows differently depending on where you are relative to the black hole. This isn't an illusion. It's a consequence of Einstein's general relativity. Gravity warps spacetime. And near a black hole, that warping becomes extreme. Once inside the event horizon, something even stranger happens. Space and time swap roles. Outside the horizon, you can move freely through space, but you're forced to move forward in time. Inside the horizon, you're forced to move inward through space, toward the singularity, and there's nothing you can do to stop it. You fall toward the singularity as inevitably as you normally move forward in time. There's no turning back, no escaping. The singularity is in your future, and you will reach it just as surely as you will experience the next moment. What happens at the singularity? We don't know. Our physics breaks down completely. General relativity predicts that matter is compressed to infinite density at a single point. But infinite density isn't a physical concept we can make sense of. Most physicists believe that quantum effects, which general relativity doesn't account for, become important at such extreme scales. We need a theory of quantum gravity to understand what really happens, and we don't have that theory yet. Let's imagine what would happen if a stellar mass black hole, say 10 times the Sun's mass, suddenly appeared near Earth. The tidal forces, the difference in gravitational pull between Earth's near side and far side, would be enormous. Earth would be stretched and compressed simultaneously. The planet would deform, crack, and eventually be torn apart. The fragments would spiral inward toward the black hole, heating up from friction and compression until they glowed white-hot. Earth would be consumed, piece by piece, until nothing remained but a thin accretion disk of superheated plasma spiraling into the black hole. Eventually, all of Earth's mass would cross the event horizon and fall into the singularity. The entire planet, compressed into a sphere smaller than a marble, before being crushed further still into the singularity itself. But black holes don't last forever. Stephen Hawking discovered that black holes emit radiation due to quantum effects near the event horizon. This is called Hawking radiation. It's incredibly faint for large black holes, but it means that over unimaginably long timescales, black holes lose mass and eventually evaporate completely. How long does it take? For a black hole with the Sun's mass, it would take approximately 10 circumflex 67 years. That's 10 followed by 67 zeros. To put that in perspective, the universe is currently about 1.38 times 10 circumflex 10 years old. A solar mass black hole would take 10 circumflex 57 times longer than the current age of the universe to evaporate. The number is so large, it's essentially incomprehensible. The universe would be unrecognizable. All the stars would have died. Galaxies would have dispersed. Matter itself might have decayed. And still, the black hole would be evaporating, slowly radiating away its mass into the void. Supermassive black holes like TON 618 would take even longer. A black hole with 66 billion solar masses would take approximately 10 circumflex 100 years or more to evaporate. That's so far in the future that it transcends human understanding of time. It's a number with no real meaning except to say, essentially forever. Black holes represent the ultimate endpoint of gravity. Matter compressed beyond the point where any force can resist further collapse. They're regions where space-time itself is torn, where our understanding of physics fails, where the universe reveals just how extreme conditions can become. And they remind us, once again, how small and fragile Earth is. A single stellar mass black hole, an object only 10 or 20 kilometers across, could consume our entire planet and compress it into something smaller than you could hold in your hand. And the largest black holes could swallow our entire solar system without even noticing. We exist in a universe where such objects are real, where such extremes are possible. And Earth, in comparison, is nothing more than a momentary arrangement of atoms, vulnerable and small. Let's talk about something that fills every cubic centimeter of space throughout the entire universe: the cosmic microwave background radiation, or CMB. Right now, as you're reading this, you're being bathed in radiation that originated 13.8 billion years ago. This radiation has a temperature of approximately 2.7 Kelvin. That's 2.7 degrees above absolute zero, or about minus 270 degrees Celsius. It's cold, incredibly cold, but it's everywhere. This radiation is the afterglow of the Big Bang itself. In the first moments after the Big Bang, the universe was unimaginably hot and dense, so hot that matter couldn't form. Protons and electrons existed, but they couldn't combine into atoms because the temperature was too extreme. The universe was filled with a plasma of charged particles and photons, all bouncing off each other continuously. Light couldn't travel freely because it was constantly being absorbed and re-emitted by the plasma. Then, about 380,000 years after the Big Bang, the universe had expanded and cooled enough for protons and electrons to combine into neutral hydrogen atoms. This moment is called recombination. And at that instant, light was suddenly free to travel through space without constantly colliding with charged particles. The universe became transparent. The photons from that moment have been traveling through space ever since, cooling as the universe expanded, until today they reach us as microwave radiation at 2.7 Kelvin. When you map the CMB across the entire sky, you're seeing the universe as it was 380,000 years after the Big Bang. You're looking at a snapshot of the infant universe. And what that snapshot reveals is remarkable. The CMB is incredibly uniform. The temperature is almost exactly the same in every direction you look. Almost. There are tiny variations, fluctuations of only about 0.00001 degrees, 100,000th of a degree. That's how smooth the early universe was. But here's what makes those tiny variations profound. Those small temperature differences represented regions where matter was slightly more or less dense than average. And those small density differences, amplified by gravity over billions of years, became the seeds of all cosmic structure. The slightly denser regions pulled in more matter, becoming denser still, eventually forming the first stars, then galaxies, then galaxy clusters, then superclusters. Everything we see in the universe today, all the structures spanning billions of light years, originated from temperature variations of 0.00001 degrees in the CMB. Without those variations, the universe would have remained perfectly uniform. No structures would have formed. No galaxies, no stars, no planets, no life. The fact that the CMB isn't perfectly smooth is why we exist. Now let's address something that confuses many people. Where is the center of the universe? Where did the Big Bang happen? The answer is everywhere and nowhere. The Big Bang didn't happen at a point in space. It happened everywhere simultaneously. Every point in the universe was the location of the Big Bang, including the point where Earth is right now. This seems impossible, but it makes sense when you understand what the Big Bang really was. It wasn't an explosion in space. It was an expansion of space itself. Imagine the universe as the surface of a balloon. As you inflate the balloon, every point on the surface moves away from every other point. But there's no center on the surface. If you're an ant living on the balloon's surface, you'd see all other ants moving away from you as the balloon expands. And every ant would see the same thing from their perspective. Each ant could claim to be at the center, because from their viewpoint, everything is moving away from them. That's what's happening with the universe. Space itself is expanding, carrying galaxies apart. Galaxies aren't moving through space. Space is expanding, and galaxies are being carried along with it. This is often described with the raisin bread analogy. Imagine a loaf of bread dough with raisins scattered throughout. As the dough rises, the raisins move apart from each other, not because they're moving through the dough, but because the dough itself is expanding. From any raisin's perspective, all the other raisins are moving away. That's the universe. We're the raisins. Space is the dough. Currently, the universe is doubling in size approximately every 10 billion years. That rate is accelerating, which we'll discuss in a moment. But think about what this means. In 10 billion years, every distance in the universe will be twice as large as it is now. The distance to Andromeda, currently 2.5 million light-years, will be 5 million light-years. The distance to the edge of the observable universe will have doubled. Space itself will have stretched, carrying everything with it. But here's where things get mysterious. When astronomers measured the expansion rate of the universe, they discovered something unexpected. The universe isn't just expanding, it's accelerating. The expansion is getting faster over time. This shouldn't happen. Gravity should be slowing the expansion down as galaxies pull on each other. But instead, something is pushing space apart, causing the expansion to speed up. We don't know what that something is. We call it dark energy, and it comprises approximately 68% of the universe's total energy content. 68%. More than two-thirds of everything in the universe is this mysterious dark energy that we can't see, can't detect directly, and don't understand. We only know it exists because of its effect on the universe's expansion. Dark energy is the biggest mystery in cosmology. We have theories. Maybe it's a property of space itself, a vacuum energy that pushes space apart. Maybe it's a new kind of field permeating the universe. Maybe it's something even stranger that we haven't imagined yet. But we don't know. And until we understand dark energy, we don't truly understand the universe. Then there's dark matter, another mystery. When astronomers measure the motion of stars in galaxies and the motion of galaxies in clusters, they find something strange. There isn't enough visible matter to account for the gravitational effects they observe. Stars in galaxies orbit faster than they should, based on the mass of visible matter. Galaxies in clusters move faster than expected. Something with mass is there, pulling on everything gravitationally, but we can't see it. This invisible mass is called dark matter, and it makes up approximately 27% of the universe's total energy content. We can't see dark matter because it doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all. The only way we know it exists is through its gravitational effects. We can see it bending light from distant galaxies through gravitational lensing. We can measure its influence on galaxy rotation curves, but we can't detect the particles themselves. Not yet. So here's where we stand. The universe is made of negative 5% ordinary matter, the stuff we can see. Stars, planets, gas, dust, everything made of atoms. 27% dark matter, invisible matter that we detect only through gravity. Negative 68% dark energy, a mysterious force accelerating the universe's expansion. We understand only 5% of what the universe is made of. The rest is unknown. When we look out at the cosmos, we're seeing only a tiny fraction of what's actually there. Most of the universe is invisible to us, detectable only through indirect effects. And Earth? Earth is made of ordinary matter, the 5%. We're not just small in size. We're made of the minority component of the universe. Everything we've ever seen, every star in the night sky, every galaxy captured by our telescopes, all of it is only 5% of what exists. The universe is stranger and more mysterious than it appears. This is the ultimate context for Earth's smallness. We're a tiny planet made of ordinary matter in a universe dominated by things we don't understand. We exist in the 5%, on a world so small it's invisible from cosmic distances, orbiting a star in a galaxy that's one among trillions. And the universe itself is mostly made of substances we can't see and forces we can't explain. We're not just small, we're rare, temporary, and made of the universe's minority ingredients. And yet, we're conscious. We can observe all of this. We can measure dark matter's effects and detect dark energy's influence. We can look back in time by observing the CMB and see the universe as it was 13.8 billion years ago. From our tiny vantage point, we've managed to map and measure nearly the entire observable universe. That's extraordinary. Size isn't everything. Understanding matters too. And somehow, from this impossibly small world, we've come to understand cosmology on the largest scales imaginable. Let's make this crystal clear. Everything you can see, everything you've ever experienced, every atom in your body, every star in the night sky, every planet, every galaxy captured by our most powerful telescopes, all of it represents only 5% of the universe. 5%. Ordinary matter, the stuff made of atoms, is the minority component of reality. We live in a universe where 95% of everything is invisible and unknown. We don't know what 95% of the universe actually is. Let that sink in. We've sent probes to other planets. We've mapped the cosmic microwave background. We've observed galaxies billions of light years away. We've measured the universe's expansion rate. We understand nuclear fusion, quantum mechanics, general relativity. We've split atoms and detected gravitational waves. And despite all of that, we don't know what most of the universe is made of. Dark matter and dark energy dominate the cosmos, and we can only detect them through their effects. We can't see them. We can't capture them. We barely understand them. The total mass energy of the observable universe is approximately 10 circumflex 53 kilograms. That's 10 followed by 53 zeros. It's written in scientific notation because the number is too large to comprehend otherwise. Every galaxy, every star, every planet, every particle of dark matter, every bit of dark energy, add it all together, and you get roughly 10 circumflex 53 kilograms. Earth's mass is about 6 times 10 circumflex 24 kilograms. So Earth's mass compared to the observable universe is approximately 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000%. That's 36 zeros after the decimal point before you reach the first significant digit. Earth isn't just a small fraction of the universe. It's an infinitesimally small fraction. You could remove Earth entirely, and the universe's total mass wouldn't change in any measurable way. Now let's explore scale through probability and combinations, because sometimes numbers reveal perspective in unexpected ways. There are more possible configurations of a standard 52-card deck than there are atoms on Earth. A deck of cards can be shuffled into 52 factorial different orders. That's 52 times 51 times 50, all the way down to 1. The result is approximately 8 times 10 circumflex 67. That's 80 followed by 66 zeros. Earth contains roughly 10 circumflex 50 atoms. The number of possible card arrangements exceeds the number of atoms on Earth by a factor of about 10 circumflex 17. Every time you shuffle a deck of cards thoroughly, you're almost certainly creating an arrangement that has never existed before in the history of the universe and will never exist again. Here's another perspective. There are more atoms in a single glass of water than there are glasses of water in all of Earth's oceans. A typical glass of water contains about 250 milliliters. That's roughly 8 times 10 circumflex 24 water molecules. And since each water molecule has 3 atoms, that's about 2.4 times 10 circumflex 25 atoms. Earth's oceans contain about 1.335 billion cubic kilometers of water. Convert that to glasses, and you get roughly 10 circumflex 21 glasses. So there are about 10,000 times more atoms in one glass than there are glasses in all the oceans. If you poured a glass of water into the ocean, let the oceans mix completely, and then scooped out another glass somewhere else, that new glass would contain approximately 100 atoms from your original glass. The numbers are that large. Now let's return to the planets, because Earth's smallness becomes even more apparent when we compare it to weather phenomena on other worlds. Jupiter's Great Red Spot, a storm that's been raging for at least 400 years, is larger than Earth, larger than our entire planet. 3 Earths could fit inside this storm. Imagine that. A weather pattern, a hurricane essentially, that could swallow 3 Earth-sized worlds, and it's been spinning continuously for centuries. The oldest continuously observed feature in the solar system, besides the planets themselves, is a storm on Jupiter. The winds at the edges of the Great Red Spot reach about 400 kilometers per hour. That's fast, but not extreme by Jupiter standards. The storm persists because Jupiter has no solid surface to slow it down. On Earth, hurricanes weaken rapidly once they move over land. On Jupiter, there's no land. The storm just continues indefinitely, powered by Jupiter's internal heat. Saturn has something even stranger. At its north pole, there's a hexagonal storm, a hexagon. 6 nearly straight sides forming a geometric shape in the clouds. Each side of this hexagon is approximately 13,800 kilometers long. That's wider than Earth's diameter. Earth is 12,742 kilometers across. This hexagon is larger, and it's been there for decades, possibly much longer. We've observed it since the Voyager missions in the 1980s, and it's still there, still hexagonal, still spinning. No one fully understands why it's hexagonal. Storms on Earth are circular or spiral-shaped, but on Saturn, under different atmospheric conditions and rotation rates, the fluid dynamics somehow create this 6-sided structure. It's stable. It rotates once every 10.5 hours, and it dwarfs Earth. Neptune, the most distant planet, has storms that come and go. When Voyager 2 flew past Neptune in 1989, it observed a massive storm called the Great Dark Spot. This storm was larger than Earth. The spot was roughly 13,000 kilometers by 6,600 kilometers. Earth, at 12,742 kilometers in diameter, could have fit inside it. The storm had wind speeds up to 2,100 kilometers per hour, the fastest winds measured anywhere in the solar system. But when the Hubble Space Telescope looked at Neptune in 1994, just 5 years later, the Great Dark Spot had disappeared. Gone. A storm larger than Earth had vanished in less than 5 years. New storms have appeared since then, some also Earth-sized or larger, but they come and go. Neptune's atmosphere is violent and unpredictable, producing transient storms that dwarf our entire planet. These comparisons hammer home a simple truth. Earth isn't just small compared to stars and galaxies. It's small compared to weather patterns on other planets. A storm on Jupiter is larger than our world. A geometric feature on Saturn is wider than our diameter. A temporary storm on Neptune exceeded our size. We exist in a solar system where even atmospheric phenomena on other planets make Earth look modest. And these planets, Jupiter, Saturn, Neptune, they're not special. They're just the gas giants in our solar system. There are likely billions of similar planets throughout the galaxy, billions of worlds with storms larger than Earth, with features that would swallow our planet whole. Earth is one rocky world among countless others, dwarfed not just by stars and galaxies, but by the very atmospheres of larger planets. This is what scale means. It's not just that Earth is small compared to the observable universe. It's that Earth is small at every level of comparison. Small compared to the Sun, small compared to giant planets, small compared to storms on those planets, small compared to stars, tiny compared to galaxies, invisible compared to superclusters, non-existent compared to the observable universe. At every step, Earth shrinks, and at no point does it ever seem large, except when you're standing on it, looking around, feeling the solid ground beneath your feet. But even that solidity is an illusion. You're standing on a thin crust of rock floating on molten magma, on a planet that's one small world among countless trillions, in a universe dominated by invisible dark matter and dark energy that we don't understand. You're made of the 5% minority component, standing on a speck, looking out at a cosmos that's mostly unknown. That's the reality of Earth's place in the universe. Let's look at our Sun more closely, because even this average star has features that dwarf Earth. The Sun's corona, its outer atmosphere, extends millions of kilometers into space. During a total solar eclipse, You can see the corona as a white halo around the blocked sun. But here's what's strange. The corona is hotter than the sun's surface, much hotter. The surface temperature is about 5,500 degrees Celsius. The corona reaches temperatures of 1 to 2 million degrees Celsius. Somehow, moving away from the heat source makes things hotter. Scientists still don't fully understand why. It likely involves magnetic fields and energy transfer mechanisms we're still working to comprehend. The sun isn't calm, it's violent. Solar flares, sudden releases of magnetic energy, can release power equivalent to millions of nuclear bombs in just a few minutes. Millions. These flares accelerate particles to nearly the speed of light and blast X-rays and gamma rays into space. When directed at Earth, they can disrupt satellites, radio communications, and power grids. But solar flares are nothing compared to coronal mass ejections, or CMEs. These are massive eruptions of plasma and magnetic field from the sun's corona. Billions of tons of material are hurled into space at speeds up to several million kilometers per hour. When a CME hits Earth, it compresses our magnetic field, inducing currents in power lines and potentially damaging transformers. In 1859, the most powerful geomagnetic storm ever recorded hit Earth. It's called the Carrington event, named after astronomer Richard Carrington, who observed the solar flare that caused it. The coronal mass ejection reached Earth in just 17 hours, far faster than normal. The induced currents were so strong that telegraph systems failed across Europe and North America. Telegraph operators received electric shocks, telegraph paper caught fire, and auroras, normally visible only near the poles, appeared as far south as the Caribbean and Hawaii. People in the Rocky Mountains woke up at night thinking it was dawn, because the sky was so bright. If a Carrington-level event hit today, the damage would be catastrophic. Our modern infrastructure is far more vulnerable than Victorian-era telegraph systems. Satellites would be damaged or destroyed. GPS would fail. Power grids could experience cascading failures as transformers burn out. Estimates suggest the economic damage could exceed several $1 trillion. Repairs could take months or years. And we'd have very little warning, maybe a day or two at most. And here's the terrifying part. The Carrington event wasn't even the worst the sun can do. In 2012, the sun produced a solar flare and CME approximately 50 times more powerful than the Carrington event. 50 times. If that eruption had been directed at Earth, the consequences would have been devastating. Fortunately, it missed us. The CME traveled through a part of space where Earth wasn't, but it could easily have hit us. We got lucky. Our sun, average as it is, has the potential to disrupt modern civilization with a single burp of energy. And we can't stop it. We can only watch, hope for warnings, and try to prepare. Earth exists at the mercy of the sun's activity, dependent on its stability for our survival. Now let's look at stars that make our sun seem pathetic. VY Canis Majoris is another red supergiant, similar to Betelgeuse, but possibly even larger. If you placed VY Canis Majoris where our sun is, it would extend past Jupiter's orbit, possibly reaching Saturn. Saturn orbits at about 1.4 billion kilometers from the sun. VY Canis Majoris's radius would span that distance. Earth, at 150 million kilometers from the sun, would be deep inside this star. We wouldn't be orbiting it. We'd be embedded in its outer layers, vaporized instantly. Antares, the red supergiant marking the heart of Scorpius, is approximately 883 times the sun's diameter, about 10,000 times more luminous. If Antares replaced our sun, Earth's orbit would be inside the star. We wouldn't see a sun in the sky. We'd be surrounded by a glowing red plasma. The star would fill the entire sky in every direction. There'd be no day or night, just endless light from all around, and the heat would incinerate everything instantly. These red supergiants, are old stars nearing the end of their lives. They've exhausted the hydrogen in their cores and are burning heavier elements. Their outer layers have expanded to enormous sizes, cooled and turned red. They're dying, slowly collapsing and expanding in cycles, eventually destined to explode as supernovae. When they do, they'll outshine entire galaxies for weeks. But red supergiants aren't the most luminous stars. Blue supergiants are. Rigel, in the constellation Orion, is a blue supergiant approximately 120,000 times more luminous than our Sun. 120,000 times. Rigel is only about 79 times the Sun's diameter, much smaller than red supergiants, but it's far hotter. Its surface temperature reaches about 11,000 degrees Celsius, twice the Sun's temperature. That heat makes it incredibly bright. If Rigel replaced our Sun, Earth would be bathed in so much radiation that our oceans would boil away in minutes. The surface would melt. The atmosphere would be stripped away. Earth would become a lifeless cinder, orbiting a blazing blue giant. And from any reasonable distance, Rigel would be painfully bright. You couldn't look at it directly even for a fraction of a second without damaging your eyes. But even Rigel isn't the most luminous star we know. That honor goes to R136A1, a star located in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way. R136A1 is approximately 8.7 million times more luminous than our Sun. 8.7 million. This star shines with the brightness of nearly 9 million suns combined. It's one of the most massive stars known, with about 215 times the Sun's mass. And it's incredibly hot, with a surface temperature around 50,000 degrees Celsius. R136A1 is so luminous that if it were 10 light-years from Earth, roughly twice the distance to Sirius, it would appear brighter in our sky than the Sun currently does. It would be blinding. We'd need to shield ourselves from its light, and that's from 10 light-years away. From Earth's current distance from the Sun, R136A1 would be so bright it would vaporize our planet instantly. These stars exist right now. R136A1 is out there, shining with the power of nearly 9 million suns. VY Canis Majoris is out there, large enough to swallow Saturn's orbit. Antares is out there, 10,000 times brighter than our Sun. And our Sun, which seems so dominant in our sky, which provides all the energy for life on Earth, is tiny and dim compared to these stellar monsters. Earth orbits a mediocre star, not a dwarf, but not a giant either. An average middle-aged yellow star that will burn steadily for billions of years. This is probably good for us. If Earth orbited a massive blue supergiant, that star would burn through its fuel in only a few million years. Not enough time for complex life to evolve. If we orbited a red supergiant, we'd be inside it. Our Sun's mediocrity is what makes Earth's existence possible. But that mediocrity also means we're not special. There are hundreds of billions of stars in the Milky Way. Most are smaller and dimmer than the Sun. Many are similar. Some are larger and brighter. And a few, like R136A1, are absolute monsters. Our Sun is one star in that distribution, unremarkable. And Earth, orbiting this unremarkable star, is even less remarkable. When you look at the night sky, every star you see is a sun. Most have their own planets. And around those planets, if life exists, beings might be looking back at our Sun as just another faint point of light in their sky. They wouldn't know Earth exists. They couldn't see our planet even with their most powerful telescopes. To them, our Sun is just one more star among billions, and we're invisible, orbiting an average star in an ordinary galaxy lost in the vastness of space. R136A1, that monster star shining with the power of 8.7 million suns, is so luminous and so hot that it's literally tearing itself apart. Over its lifetime, which has only been a few million years so far, it has lost mass equivalent to approximately 50 suns through stellar winds. 50 suns worth of material blown off into space by the sheer intensity of its radiation. The star is so bright that the pressure from its light pushes its outer layers away. It's evaporating itself slowly but inexorably, and it will continue losing mass until eventually it explodes as a supernova, one of the most violent events in the universe. Eta Carinae is another unstable monster. This star system, located about 7,500 light-years from Earth, goes through periodic outbursts where it ejects enormous amounts of material. During these outbursts, which happen every few decades to centuries, Eta Carinae ejects mass equal to Earth's mass approximately every 1,000 years. Think about that. Our entire planet, everything on it, every atom ejected as stellar wind, over a millennium. The star is surrounded by the Homunculus Nebula, a vast cloud of ejected material shaped like an hourglass. This nebula contains several times the Sun's mass in material that Eta Carinae has blown off in relatively recent history. Eta Carinae is a ticking time bomb. It could explode as a supernova at any time. When it does, it'll be one of the brightest stellar events visible from Earth in recorded history. Which brings us to Betelgeuse. We've mentioned this red supergiant before, but let's talk about what happens when it dies. Betelgeuse is approximately 548 light-years from Earth. That's close by cosmic standards, and it's nearing the end of its life. When it finally explodes as a supernova, and this could happen any time in the next 100,000 years, it'll be visible during the daytime on Earth. You'll be able to see a bright point of light in the sky, even when the sun is up. At night, Betelgeuse will be one of the brightest objects in the sky, possibly rivaling the full moon in brightness. It'll cast shadows at night, and this will last for weeks or months before gradually fading. It won't harm us. At 548 light-years, Betelgeuse is too far away for its supernova to cause significant damage to Earth. But it'll be spectacular. A star visible to the naked eye in Orion will suddenly become brilliant, announce its death in a blaze of light, then slowly fade away, leaving behind either a neutron star or a black hole. But supernovae can be dangerous if they're close enough. A supernova approximately 50 light-years away or closer could potentially cause a mass extinction on Earth. The radiation, particularly gamma rays, would strip away part of Earth's ozone layer. This would expose the surface to increased ultraviolet radiation from the sun. Marine ecosystems would be devastated as phytoplankton died. The food chain would collapse from the bottom up. Some scientists think past mass extinctions might have been triggered by nearby supernovae, though the evidence is circumstantial. Fortunately, there are no massive stars close enough to threaten us with a supernova in the foreseeable future. Betelgeuse, at 548 light-years, is the closest star likely to explode soon, and it's far enough that we're safe. We can enjoy the show without worrying about consequences. The closest supernova in recent history, at least observed in recent history, was SN 1987A. This supernova occurred in the Large Magellanic Cloud, approximately 168,000 light-years from Earth. On February 23, 1987, astronomers detected a sudden brightening. A star had exploded, but the light from that explosion had been traveling for 168,000 years before reaching Earth. The star actually exploded 168,000 years ago, long before modern humans existed. We were just seeing the delayed notification. The star had been dead for longer than our species has existed, and we only found out about it in 1987. This illustrates something profound about looking at the universe. We're always seeing the past. Every star in the night sky you're seeing as it was years, decades, centuries, or millennia ago. The farther away something is, the further back in time you're seeing. When you look at the Andromeda Galaxy, 2.5 million light-years away, you're seeing it as it was 2.5 million years ago, before humans existed. That galaxy has changed in the meantime, but we won't see those changes for millions of years. Now let's talk about what supernovae really are in terms of energy. A supernova releases more energy in its first few seconds than our Sun will produce in its entire 10 billion year lifetime. More energy in seconds than 10 billion years of steady fusion. The numbers are so extreme, they lose meaning. When a massive star's core collapses, the implosion rebounds, sending a shockwave through the star's outer layers. That shockwave heats the material to billions of degrees and accelerates it to a significant fraction of the speed of light. The star explodes with such violence that it outshines its entire galaxy for weeks. Historically, several supernovae have been visible to the naked eye from Earth. In 16 CE, a supernova appeared in the constellation Lupus. SN 1600 was so bright that people could read by its light at night. It was brighter than Venus, the brightest object in the sky besides the sun and moon. The supernova remained visible for months, gradually fading over the course of a year. This stellar explosion happened about 7,200 light-years away. From that distance, it was still bright enough to cast shadows at night. In 1054 CE, another supernova appeared in the constellation Taurus. Chinese and Arab astronomers recorded it carefully. This supernova was visible during the daytime for 23 days. 23 days of being able to see a star during daylight hours. At night, it was one of the brightest objects in the sky. This supernova created the Crab Nebula, a vast expanding cloud of stellar debris that we can still see today, nearly 1,000 years later. The nebula is about 11 light-years across now, and still expanding at thousands of kilometers per second. But here's what makes supernovae personally relevant. Every atom heavier than iron in your body was forged in a supernova explosion. Not just any supernova, multiple supernovae over billions of years. Let me explain. The early universe, right after the Big Bang, contained only hydrogen, helium, and traces of lithium. That's it, the lightest elements. Everything heavier, carbon, nitrogen, oxygen, silicon, iron, gold, uranium, all of it was created later inside stars. Stars fuse hydrogen into helium, then helium into carbon and oxygen. Massive stars continue fusing heavier elements. Carbon into neon and magnesium. Neon into oxygen and magnesium. Oxygen into silicon and sulfur. Silicon into iron. But fusion stops at iron. Iron is the most stable nucleus. Fusing iron costs energy instead of releasing it. So stars build up iron cores, and those cores eventually collapse, triggering supernovae. In the supernova explosion, the temperatures and pressures are so extreme that atoms are smashed together, creating elements heavier than iron. Gold, platinum, uranium, all the heavy elements are forged in these explosions. Then the supernova blasts this material into space, enriching the interstellar medium. Eventually, that enriched gas collapses to form new stars and planets. Our Sun is a third-generation star, formed from gas that had already been through at least 2 previous cycles of stellar birth and death. The atoms in your body, the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created in stars, and the heaviest atoms, the gold in jewelry, the iodine in your thyroid, were created in supernova explosions. You are literally made of stardust, ancient stellar explosions. The atoms in your left hand might have come from a different supernova than the atoms in your right hand. You're a collection of stellar debris, assembled billions of years later into a conscious being on a small planet orbiting an average star. Every breath you take contains atoms that were once inside a star. Every thought you think happens because of atomic interactions involving elements forged in stellar furnaces. This connection between us and the stars isn't poetic metaphor. It's literal truth. We are the universe made conscious. We are stardust that has learned to think, to wonder, to ask questions about its own origins. The iron in your blood, essential for carrying oxygen, was forged in a supernova explosion billions of years before Earth existed. That iron drifted through space, eventually accumulating in the nebula that became our solar system, then incorporating into Earth, then into life, then into you. Every person you've ever met is made of ancient stellar explosions. Every living thing on Earth. We're all recycled star matter, temporarily organized into biological forms, conscious for a few decades, then returning to simpler forms when we die. The atoms persist. They'll eventually be incorporated into other things, other beings perhaps, or simply drift as dust. But they were forged in stars, and that origin connects all of us to the cosmos in the most fundamental way. Earth isn't just small. It's a collection of stellar debris, a temporary arrangement of atoms that will eventually disperse. And we, living on this small world, are also temporary arrangements of those same atoms. We're not separate from the universe, observing it from outside. We're part of it, made of it, conscious pieces of the cosmos, examining itself. And that realization, more than anything else, captures what it means to understand Earth's place in the universe. Right now, as you're reading this, cosmic rays are passing through your body. High-energy particles, mostly protons, accelerated to nearly the speed of light by supernova explosions and other violent cosmic events. These particles slam into Earth's atmosphere constantly, creating showers of secondary particles. Some of those particles reach the ground and pass through you. Every second. Thousands of them. They pass through your brain, your heart, your bones, mostly without interacting. Occasionally, one collides with an atom in your body, potentially causing DNA damage. This happens to everyone, everywhere, all the time. We're constantly being bombarded by remnants of stellar explosions that happened thousands or millions of years ago. But cosmic rays are nothing compared to neutrinos. Approximately 100 billion neutrinos from the Sun pass through your thumbnail every second. 100 billion. Through just your thumbnail. Scale that up to your entire body, and trillions upon trillions of solar neutrinos are passing through you every second. Right now. And you don't feel anything, because neutrinos barely interact with matter. Neutrinos are so weakly interacting that they could pass through a light year of solid lead without being stopped. A light year. That's about 9.46 trillion kilometers of lead, and neutrinos would pass through it like it wasn't there. Most of the neutrinos passing through Earth don't interact with a single atom. They enter on one side, pass through the entire planet, and exit the other side without ever hitting anything. To a neutrino, solid matter is almost completely transparent. The Sun produces neutrinos as a byproduct of nuclear fusion in its core. These neutrinos stream outward in all directions at the speed of light. They don't interact with the Sun's outer layers. They just pass straight through and out into space. 8 minutes later, trillions of them pass through Earth and through you. When a star goes supernova, approximately 99% of the energy is released as neutrinos. Not light, not kinetic energy, neutrinos. The visible explosion, the part we can see, represents only about 1% of the total energy. The rest, the vast majority, escapes as neutrinos in the first few seconds of the collapse. These neutrinos carry away so much energy that they can be detected on Earth even from supernovae in other galaxies. When SN 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth registered a burst of neutrinos from the supernova. Only about 20 neutrinos were detected out of trillions that passed through Earth. But that was enough to confirm that the neutrinos arrived hours before the visible light, exactly as predicted by theory. Now let's talk about gold. We said earlier that elements heavier than iron are created in supernovae. That's mostly true, but there's an exception. The heaviest elements, including gold, platinum, and uranium, require even more extreme conditions than ordinary supernovae provide. These elements are created primarily in neutron star collisions. When two neutron stars orbit each other, they gradually lose energy by emitting gravitational waves. Eventually, they spiral together and merge in a violent collision. The temperatures and densities in that collision are so extreme that heavy elements are forged and ejected into space. In 2017, astronomers detected gravitational waves from a neutron star merger approximately 130 million light-years away. This was the first neutron star collision ever observed. The gravitational waves were detected by LIGO and Virgo observatories. Telescopes around the world immediately pointed at the location, and they saw something remarkable: a kilonova, an explosion powered by radioactive decay of heavy elements. Analysis of the light from this kilonova revealed that the collision had created approximately 10 Earth masses of gold, 10 times Earth's mass in pure gold, forged in seconds and blasted into space. This single collision produced more gold than exists in Earth's entire crust. All the gold ever mined by humans, all the gold in jewelry, in electronics, in vaults, all of it combined is only about 200,000 tons, a tiny fraction of what this one neutron star merger created. The collision also produced platinum, uranium, and other heavy elements in enormous quantities. This is where the gold in your jewelry came from. Not from an ordinary supernova, from neutron star collisions billions of years ago. That 2017 event also confirmed that gravitational waves travel at the speed of light, exactly as Einstein predicted. Gravitational waves are ripples in space-time itself, caused by accelerating massive objects. When two black holes or neutron stars orbit each other, they create waves that propagate outward at light speed, carrying energy away from the system. These waves are incredibly weak by the time they reach Earth. The 2017 neutron star merger, despite being enormously violent, caused space-time to flex by less than the width of a proton when the waves passed through Earth. The first gravitational wave detection happened on September 14, 2015. LIGO detected ripples in space-time from two black holes merging approximately 1.3 billion light-years away. These black holes, with masses of 29 and 36 times the Sun, have been orbiting each other for millions or billions of years. As they spiraled closer, they emitted gravitational waves, losing energy and angular momentum. In the final fraction of a second, they merged into a single black hole, with a mass of about 62 times the Sun. Wait, 29 plus 36 equals 65. But the final mass was only 62 solar masses. What happened to the other 3 solar masses? They were converted directly into gravitational wave energy, 3 times the mass of the Sun, completely converted to pure energy in the form of space-time ripples, radiated away in less than 1 second. For that brief moment, the merger released more power than all the stars in the observable universe combined. Not more total energy, but more power. More energy per second. This is what E equals mc quadrant means in practice. Mass can be converted to energy, and when it is, the amounts are staggering. 3 solar masses, roughly 6 times 10 circumflex 30 kilograms, converted to energy according to E equals mc quadrant. The result is approximately 5 times 10 circumflex 47 joules. That's 5, followed by 47 zeros, released in less than 1 second. The peak power output during the final moments of the merger was about 10 circumflex 49 watts. For comparison, the Sun's total power output is about 4 times 10 circumflex 26 watts. The merger was roughly 10 circumflex 23 times more powerful than the Sun, 10,000 billion times more powerful. And this happened 1.3 billion light-years away. The collision occurred 1.3 billion years ago, when life on Earth was still mostly single-celled organisms. The energy radiated outward as gravitational waves traveling at the speed of light, crossing the vast distances between galaxies. And on September 14, 2015, those waves finally reached Earth, causing our detectors to flex by an imperceptible amount, recording the echo of a cataclysmic event from the early universe. We live in a universe where such events are common. Neutron stars merge, black holes collide, supernovae explode, stars tear themselves apart, and all of it releases energies that dwarf anything we experience on Earth. A single neutron star merger releases more energy in seconds than our sun will produce in its entire lifetime. A supernova outshines an entire galaxy. These are the processes that forged the elements we're made of, that created the gold we value, that shaped the universe we observe. And Earth? Earth is a quiet backwater where these violent processes happened billions of years ago, far enough away that the results reached us as nothing more than a gentle rain of heavy atoms incorporating into our planet's formation. We're the beneficiaries of cosmic violence, living peacefully on a small world made of ancient stellar explosions and neutron star collisions. The atoms in your body have witnessed events we can barely imagine. They've been inside stars. They've passed through supernova explosions. They've drifted through space for eons. And now they're temporarily arranged into you, conscious and wondering about their own history. This is the context for Earth's existence. We're not just small in space. We're temporary arrangements of matter that's been recycled through the most violent processes in the universe. Everything around you, everything you've ever touched, came from stars. And everything will eventually return to simpler forms, perhaps to be incorporated into new stars, new worlds, new beings billions of years from now. We're part of a cosmic cycle of creation and destruction that's been ongoing for 13.8 billion years and will continue for trillions more. Earth is one small stage in that vast cycle, and you're one temporary actor, performing briefly before the atoms that make you are recycled into something else. Let's be absolutely clear about what that 2015 black hole merger accomplished. At its peak, for a fraction of a second, that merger produced more power than all the stars in the observable universe combined. More than 200 billion trillion stars, all shining simultaneously, couldn't match the power output of those two black holes colliding. For that brief moment, the merger was the brightest event in the universe, not in visible light, but in gravitational waves. It was louder, in the gravitational sense, than everything else happening in the cosmos at that instant, and we detected it. From 1.3 billion light-years away, the waves had weakened enormously by the time they reached Earth, but our instruments were sensitive enough to catch them. This opens a new way of observing the universe. We're not just seeing electromagnetic radiation anymore. We're feeling the fabric of space-time itself vibrating. There's something even more remarkable we might detect eventually. Gravitational waves from the Big Bang itself. The first moments of the universe's expansion should have created gravitational waves, and those waves might still be detectable today, encoded in subtle patterns in the cosmic microwave background radiation. If we can detect them, they'd give us a window into the universe's first fraction of a second, a time when the universe was so hot and dense that matter as we know it couldn't exist. This is one of the frontiers of modern cosmology. We're trying to detect ripples in space-time from 13.8 billion years ago, looking for echoes of the universe's birth. Now let's talk about what telescopes have revealed about just how full the universe really is. In 1995, astronomers pointed the Hubble Space Telescope at what appeared to be an empty patch of sky, no bright stars, no obvious galaxies, just darkness. They left the telescope pointed at this tiny region for 10 days, collecting as much light as possible. When they processed the images, they found approximately 3,000 galaxies. 3,000 in a patch of sky that appeared empty to the naked eye. This patch was tiny, about 1/24 millionth of the total sky. Imagine holding a drinking straw at arm's length and looking through it. That's roughly the size of the region Hubble observed, and in that tiny field of view, 3,000 galaxies, each one containing hundreds of billions of stars. The image became known as the Hubble Deep Field, and it fundamentally changed our understanding of the universe's galaxy density. Later, in 2004, Hubble observed an even smaller region for even longer. The Hubble Ultra Deep Field captured approximately 10,000 galaxies in an area of sky even tinier than the original Deep Field. 10,000 galaxies in a region so small you'd need dozens of them to cover the full moon. Every direction you look, if you look deep enough, you find thousands upon thousands of galaxies. Some of the galaxies in these images are approximately 13 billion light-years away. We're seeing them as they were 13 billion years ago, only about 700 million years after the Big Bang. These are ancient infant galaxies, forming their first stars, assembling their first structures. They're small and chaotic compared to modern galaxies like the Milky Way, and we're seeing them frozen in time, their light having traveled for 13 billion years to reach us. These galaxies don't look like this anymore. They've had 13 billion years to evolve since the light we're seeing left them. They've probably merged with other galaxies, formed trillions more stars, perhaps developed into massive elliptical galaxies or grand spirals. But we'll never see those changes. The light showing us their current state won't reach Earth for billions of years. The deep field images revealed something profound. Statistically, there should be tens of thousands of galaxies in every direction we point a telescope, if we look deep enough. The universe isn't sparsely populated. It's packed with galaxies. Every tiny patch of sky, no matter how empty it appears, contains thousands of distant galaxies waiting to be discovered, with sufficient exposure time. The James Webb Space Telescope, launched in 2201, has pushed even further. With its infrared capabilities, it can detect galaxies from approximately 13.4 billion years ago. These are some of the first galaxies that ever formed, appearing only 300 to 400 million years after the Big Bang. The universe at that time was just beginning to transition from its dark ages, when no stars existed, to an era of rapid star formation. And here's what's remarkable about these early galaxies. They were forming stars at rates approximately 100 times faster than the Milky Way does today. 100 times. The Milky Way forms about 1 to 3 solar masses of new stars per year. These early galaxies were forming hundreds of solar masses of stars per year. They were furiously converting gas into stars, brightening rapidly, enriching themselves with heavy elements through supernovae, growing and evolving at breakneck speed. Why were they forming stars so fast? The universe was denser back then. Galaxies were closer together. Gas was more abundant and hadn't been depleted by previous generations of star formation. Conditions were ripe for rapid growth. These early galaxies were small but incredibly active. The seeds that would eventually grow into the massive galaxies we see today. The very first stars, called population 3 stars, were completely different from stars today. They formed from gas that contained only hydrogen and helium, with no heavy elements at all. Without heavy elements, the gas couldn't cool efficiently, which meant the clouds that collapsed to form stars had to be much more massive. Population 3 stars are thought to have been approximately 100 to 1,000 times more massive than our Sun, maybe more. These were monster stars, short-lived, burning incredibly hot and bright, exhausting their fuel in only a few million years. When they exploded as supernovae, they seeded the universe with the first heavy elements: carbon, oxygen, silicon, iron, all of it created for the first time in these first-generation stellar explosions. Those elements then mixed with the remaining hydrogen and helium, allowing the second generation of stars, population 2 stars, to form. These were smaller, longer-lived, and they created even more heavy elements. Eventually, third-generation stars like our Sun formed from gas that had been enriched by multiple previous generations. We've never observed a population 3 star directly. They all died billions of years ago. But we're searching for them. If James Webb or future telescopes can look deep enough, they might catch a glimpse of these first stars, the ones that lit up the universe for the first time and created the first heavy elements. It would be like seeing the universe wake up from its dark ages. All of this reinforces Earth's place in cosmic history. We're on a planet orbiting a third-generation star, formed 4.5 billion years ago, in a mature galaxy that's been around for over 13 billion years. We're late to the cosmic story. Most of the universe's stars have already formed. Most of the heavy elements have already been created. We exist in a relatively quiet era, when star formation has slowed, when galaxies have matured, when the universe has settled into a more stable state than it was in its youth. And from our vantage point on Earth, a tiny world orbiting an average star in an ordinary galaxy, we're able to look back across billions of light years and see the universe's early history. We can observe galaxies as they were 13 billion years ago. We can detect gravitational waves from black hole mergers. We can see the cosmic microwave background from 13.8 billion years ago. From this impossibly small planet, we've mapped the observable universe. That's the paradox of Earth's place in the cosmos. We're infinitesimally small, but we're also observers, conscious beings capable of comprehending scales that dwarf us by incomprehensible factors. We're tiny, but we're not insignificant, because significance isn't about size, it's about awareness. And Earth, as far as we know, is where awareness exists, where the universe examines itself, where stardust asks questions about its own origins. None of the first-generation stars, those massive population 3 giants, still exist today. Every single one exploded as a supernova within a few million years of forming. They burned so hot and so bright that they exhausted their nuclear fuel almost immediately on cosmic timescales. These stars lived fast and died young, leaving behind black holes, neutron stars, and clouds of enriched gas that would seed the next generation of star formation. We'll never see a population 3 star in the present universe. They're extinct, relics of the universe's distant past. These first stars had no heavy elements whatsoever. They were made purely of hydrogen and helium created in the Big Bang, with trace amounts of lithium. Nothing else. No carbon, no oxygen, no iron. The periodic table didn't exist yet. Everything heavier than helium had to be created inside these first stars and dispersed by their explosions. We exist in a universe that has been progressively enriched by stellar nucleosynthesis over billions of years. Every generation of stars creates more heavy elements, and those elements get incorporated into the next generation. Our Sun contains those elements because it formed late enough in cosmic history that multiple previous generations had already lived and died. Now let's look at some of the densest stellar environments in the universe. Globular clusters. These are spherical collections of hundreds of thousands of stars, all bound together by gravity, all orbiting the galaxy as a single unit. A typical globular cluster might contain 100,000 to 1 million stars packed into a sphere only about 100 light-years across. That's incredibly dense compared to the stellar neighborhood around our Sun. In the cores of globular clusters, stars are separated by only light weeks, sometimes light days. Our nearest star, Proxima Centauri, is 4.24 light-years away. In a globular cluster's core, you'd have dozens or hundreds of stars within that same distance. If you lived on a planet in a globular cluster's core, your night sky would be spectacular. Thousands of stars brighter than Venus in our sky, some so close they'd appear as disks rather than points of light. The night would never be truly dark. It would be perpetual twilight illuminated by thousands of nearby suns. Omega Centauri is one of the largest globular clusters orbiting the Milky Way. It contains approximately 10 million stars. 10 million. And it's unusual because it's so massive and so complex that many astronomers think it's not actually a globular cluster. It's probably the stripped core of a dwarf galaxy that the Milky Way consumed billions of years ago. The outer stars were torn away by tidal forces, and what remains is this dense core, now orbiting our galaxy as a captive remnant. In the dense environments of globular clusters, stellar collisions can actually happen. In normal galactic environments, stars are so far apart that collisions are nearly impossible. But in globular cluster cores, stars occasionally pass close enough that tidal forces or direct collisions occur. These collisions create exotic objects called blue stragglers. These are stars that appear younger and bluer than they should be. They've been rejuvenated by merging with another star, or by stealing mass from a companion, giving them fresh fuel to burn. They stand out in globular clusters as anomalously young-looking stars in otherwise ancient populations. Globular clusters are some of the oldest objects in the galaxy. Most are over 10 billion years old, formed when the Milky Way itself was young. They orbit the galaxy in the halo, the spherical region surrounding the disk. They're relics of the galaxy's early history, preserved snapshots of what star formation looked like billions of years ago. Now let's talk about galactic cannibalism. Because galaxies don't just exist peacefully side by side, they consume each other. Right now, as you're reading this, the Milky Way is in the process of cannibalizing the Sagittarius dwarf elliptical galaxy. This small galaxy, containing about 10 million stars, is being torn apart by the Milky Way's gravity. As it orbits, tidal forces stretch it into long streams of stars that wrap around our galaxy like ribbons. We can trace these stellar streams and map out where the dwarf galaxy has been and where it's going. Eventually, over the next few billion years, the Sagittarius dwarf will be completely absorbed. Its stars will become part of the Milky Way's halo. The dwarf galaxy will cease to exist as a distinct object. It'll be digested, its identity erased, its stars scattered throughout the Milky Way. And this isn't unusual. The Milky Way has consumed at least 15 smaller galaxies throughout its history, probably more that we haven't detected yet. Each time our galaxy encounters a smaller galaxy or dwarf galaxy, gravity takes over. The smaller galaxy is pulled apart, its stars absorbed. This is how large galaxies grow. They eat smaller ones. Andromeda, our larger neighbor, has been even more voracious. It has consumed hundreds of smaller galaxies over its history. It's a cosmic predator, growing larger by devouring everything smaller that comes too close. When we look at Andromeda, we're seeing a galaxy that has aggressively accumulated mass by consuming its neighbors. The halo around Andromeda is filled with stellar streams, the remnants of devoured galaxies stretched into thin ribbons by tidal forces. This process is ongoing throughout the universe. Large galaxies consume small ones. Medium galaxies merge to create larger galaxies. Galaxy clusters grow by attracting more galaxies. The universe's structure is built through a hierarchy of mergers and collisions, with smaller objects combining to form progressively larger ones. And in about 4.5 billion years, the Milky Way and Andromeda will merge. This will be the largest merger in our local cosmic neighborhood. Two massive spiral galaxies colliding and combining. The result will be a giant elliptical galaxy containing roughly 1 trillion stars. This new galaxy, sometimes called Milkomeda or Milkdromeda, will dominate the local group. Any surviving dwarf galaxies will orbit this new giant, waiting their turn to be consumed. During the merger, the night sky from Earth, if Earth still exists, will be spectacular. Andromeda will grow larger over millions of years, eventually filling a significant portion of the sky. The two galaxies will pass through each other, their stars intermixing. Despite containing over 1 trillion stars combined, actual stellar collisions will be rare. because stars are so far apart. But the gas clouds will collide, triggering enormous bursts of star formation. New stars will light up throughout both galaxies. The sky will be filled with bright young stars and glowing nebulae. Eventually, after multiple passes, the two galaxies will settle into a single elliptical structure. The spiral arms will be destroyed. The disk will be disrupted. What was once two organized spiral galaxies will become one chaotic elliptical galaxy with stars orbiting in random directions. This is the fate of most galaxies. They merge, they collide, they grow. The universe started with small galaxies, and over billions of years, those small galaxies have been combining into progressively larger structures. The Milky Way itself is probably the product of dozens or hundreds of mergers over the past 13 billion years. We're not a pristine original galaxy. We're an amalgamation of many smaller galaxies that combined over time. And Earth, throughout all of this, is just along for the ride. When the Milky Way consumed the Sagittarius dwarf, Earth didn't notice. When we eventually merge with Andromeda, Earth will probably be long dead, the Sun having evolved off the main sequence. But if Earth somehow survived, life on the surface wouldn't be directly affected by the merger. The stars passing by in the sky would change. New stars would appear. The view would be different, but the Sun's orbit and Earth's orbit would continue more or less unchanged. This is galaxy dynamics. Vast structures spanning hundreds of thousands of light years, colliding and merging over billions of years, and individual stars, including our Sun, are just passengers, swept along by gravitational currents too large to resist. Earth is not just small in space, it's a passive participant in processes that operate on scales billions of times larger than our planet. We don't influence galactic dynamics, we're influenced by them. And we're lucky to exist in an era and location where those dynamics happen slowly enough that we can survive. When the Milky Way and Andromeda collide, something counterintuitive will happen. Despite these two galaxies containing over 1 trillion stars combined, individual stars almost certainly won't hit each other. Not a single collision. The space between stars is simply too vast. Remember, our nearest star is 4.24 light-years away. Even in the densest parts of both galaxies, stars are separated by light-years. When the galaxies pass through each other, the stars will intermix like two swarms of bees passing through each other. Each bee, each star, will sail past countless others without ever making contact. But while the stars won't collide, the galaxies themselves will be fundamentally transformed. The collision will rearrange both galaxies completely, over approximately 2 billion years. The graceful spiral structures will be destroyed. The organized rotation will become chaotic. Stars that once orbited in neat circular paths will be flung into elliptical orbits tilted at random angles. The two disks will merge into a single elliptical blob, a galaxy with no defined structure, just stars orbiting in all directions around a common center. And our solar system will likely be flung to the outskirts of the new, merged galaxy. Computer simulations suggest there's a reasonable probability that our Sun will end up much farther from the galactic center than we are now. We might be tossed into the outer halo, far from the new galaxy's core. There's even a small chance, maybe a few percent, that we'll be ejected entirely, flung out of the galaxy altogether, becoming an intergalactic wanderer. But here's what's important. Even if our solar system is ejected from the galaxy entirely, Earth and the Sun would stay together. The gravitational bond between the Sun and its planets is much, much stronger than the weak galactic gravity that holds stars in orbit around the galactic center. To separate Earth from the Sun, you'd need something to pass extremely close, within a light-year or so, exerting tidal forces strong enough to disrupt our orbit. That's extraordinarily unlikely. So wherever the Sun goes, Earth goes with it. If we're ejected, we become a rogue solar system, drifting through intergalactic space, but still intact. This brings up something fascinating and slightly terrifying: rogue planets. planets that have been ejected from their solar systems and now wander through space alone. No star, no sunlight, just darkness. These rogue planets may actually outnumber stars in the galaxy. Some estimates suggest there could be billions of Earth-sized rogue planets wandering the Milky Way in eternal night. How do planets become rogue? Gravitational interactions. In young solar systems, planets migrate, changing their orbits as they interact gravitationally with each other and with the disk of gas and dust. Sometimes a planet gets flung outward with enough velocity to escape the star's gravity entirely, or two planets have a close encounter, and one gets ejected to save the system's gravitational energy. It's like a game of celestial billiards, and occasionally a ball gets knocked clear off the table. These rogue planets drift through the galaxy forever. If they're large enough, they might retain internal heat for billions of years, keeping a molten core and perhaps even geological activity. If they have thick atmospheres, those atmospheres might trap enough heat to maintain liquid water beneath ice shells. Some scientists speculate that rogue planets could even harbor life, organisms living in subsurface oceans, heated by residual internal warmth. We'll probably never know. These planets are nearly impossible to detect. No star illuminates them. They don't emit much heat. They're ghosts, wandering unseen through the darkness. And occasionally, one might pass through our solar system. A rogue planet entering from interstellar space could destabilize planetary orbits if it passed close enough. It wouldn't need to collide with anything. Just passing within a few AU of a planet would exert gravitational tugs, potentially changing that planet's orbit. In extreme cases, a rogue planet could eject one of our planets, sending it out into interstellar space, while the rogue planet settles into an orbit around our Sun, taking the ejected planet's place. This might have already happened, the NICE model. A theory about the early solar system's evolution suggests that our solar system once had 5 giant planets, not 4. Jupiter, Saturn, Uranus, Neptune, and a 5th ice giant. About 4 billion years ago, this hypothetical 5th planet had a gravitational encounter with Jupiter and was ejected from the solar system entirely. It's out there somewhere, a rogue ice giant that once called the Sun home, now wandering the galaxy alone. We don't know if this really happened. It's a theory that fits certain observations, like the late heavy bombardment, a period about 3.9 billion years ago when the inner solar system was pelted with asteroids and comets. The NICE model suggests this bombardment was triggered by the giant planets migrating and destabilizing the Kuiper belt, sending icy bodies hurtling inward, and that migration was caused in part by the ejection of the 5th giant planet. There's also speculation about Planet 9. For years, astronomers have noticed strange clustering in the orbits of certain distant Kuiper belt objects. Their orbits seem to be aligned in a way that's statistically unlikely unless something massive is gravitationally shepherding them. The proposed explanation is Planet 9, a hypothetical planet with a mass about 5 to 10 times Earth's mass, orbiting in the outer solar system. If Planet 9 exists, it orbits approximately 20 times farther from the Sun than Neptune. Neptune orbits at about 30 ATU. Planet 9 would be at 600 ATU or more. At that distance, its orbit would take somewhere between 10,000 and 20,000 years to complete once. 10 to 20,000 years for a single orbit, and the sunlight reaching Planet 9 would be incredibly faint. The Sun would appear as just a very bright star, providing almost no warmth. If Planet 9 exists, it's a frozen world, dark and distant, barely bound to our solar system. But does it exist? We don't know. No one has seen it directly. The evidence is indirect, based on orbital perturbations of other objects. Some astronomers think Planet 9 is real. Others think the clustering could be a statistical fluke or caused by observational bias. The search continues. If Planet 9 is out there, future telescopes might eventually spot it, a faint dot moving slowly against the background stars. Whether Planet 9 exists or not, the outer solar system is clearly more complex than we once thought. There might be objects we haven't discovered yet, dwarf planets, rogue planets, captured from interstellar space, remnants of the solar system's chaotic youth. The outer darkness holds secrets, and we've only begun exploring it. All of this reinforces how precarious Earth's existence is. We orbit at a stable distance from the Sun, protected by Jupiter's gravity from too many asteroid impacts, in a solar system that has settled into a relatively stable configuration after billions of years of chaos. But that stability isn't guaranteed forever. A rogue planet could pass through. A close encounter with another star could disrupt planetary orbits. The galaxy itself could fling us into the outer halo or eject us entirely. We exist in a Goldilocks moment, in a Goldilocks location, not too close to the galactic center, where radiation and stellar density would be dangerous, not too far out, where heavy elements would be scarce, in a stable orbit around a stable star, in a solar system that's finished its violent youth. At a time when the universe has matured enough for complex life to evolve, but hasn't expanded so much that galaxies are isolated and unreachable. Earth is small, yes, but Earth also exists in a remarkably fortunate configuration, one that has allowed life to persist for billions of years and consciousness to emerge. And that makes Earth, despite its infinitesimal size, extraordinarily precious. Not because of its physical dimensions, but because of what it contains and what it represents. The only place we know where the universe has become aware of itself.